Dear colleagues, good morning. I would like to devote this lecture to several people. First of all, to A. Vlasov, the famous mathematician and physicist in Moscow who lived in the last century and derived equations which keep busy still many mathematicians for 3 generations around the world. And I'm belonging to this group who studied Vlasov's equations in different forms. Next, I would like to dedicate this lecture to all those who have been engaged in making strong the mathematical community by organizing conferences, by cooperations between different countries, also the German and Russian relations have been reinforced, and thus have supported cooperation and friendship. Next slide. This is what I report on is joint work with my colleague E. Jörn. He did all the numerical analysis, which automatically came in. Usually I have only made papers which were theoretically oriented, but this time you will see the numerics couldn't be at all avoided. Let me make you familiar by an elementary way Vlasov's equation. I think one likes particularly elementary things before one can go to sophisticated relations. And thus I would like to remind you of the n-body problem. What is the n-body problem? I will make a sketch here. You have n particles in space, and I will draw some of them. Let this be a particle located at the space variable xk with mass mk, and then you have many other particles. I will draw a particular one with the running index j with mass mj, and now you assume that between the particles there is the Newton's law of attraction. So every particle attracts any other particle, and so the force which the kth particle exerts on the jth particle is given by the following law. It is d dxk of summation over all j unequal k of mk times mj over xk minus xj. This is the force. And now what astronomers do, they denote this. They have a minus sign here, and this, including the minus sign, is usually denoted U, the potential. And you take the negative derivative, get the force. Now, in practice, this system is untractable. If you want to solve the n-body problem, you have many problems. First of all, collisions before time on an interval which you prefix as 0t, and therefore this is not a good model to describe star systems. What they do is they use a distribution function of 7 variables. We are working in R3 here, so x is a point in R3, or v is a point in R3. And this function tells you how many particles are in the point x traveling with velocity v at time t. It's a density function. And now one can use this rough expression to go to the limit, and what you get is then this here, I mean minus integral, you exchange the summation to the integral. First of all, the mk drops later out. First of all, I would like to write the differential equations of motion for the discrete system. And this is this here. And then there comes this expression, which I have already written there. And when you now go to the limit, this all can be made precise. Then you arrive, exchanging the sum against the integral. You get an integral over R3. The mk drops out here, and I have mj. This is then in the limit the local density, all the points which are sitting in x or t, traveling with different speeds, are rho t y over x minus y dy. So this is the smoothed out potential, which is u. And then you have the negative sign here, and this is the force, right? So very roughly and very intuitively, I have given you the expression for u in our stellar dynamic case. Yes, further on, please. So not so much.
Oh.
So we arrive at the following three equations.
Don't accidentally press it.
Okay. Yeah. Now we have the system. The F in the force field given by B and the force X. This is the right-hand side, and you try to solve, or you have here the characteristic system of a differential equation, which is a continuity equation for this F, which is here. The potential I already derived. And the third is just the fact that in calculating the potential, you have to sum up all particles sitting at the point x at time t, and this gives you the local density. So you end up with a system of three equations. The second equation is simply arrived by differentiating the u, and you get Poisson's equation. So this gives you the Blasov-Poisson system supplemented by the definition. This is just the definition of the local density. Okay, once more again, F is we are looking for solutions of this system, and this is a triple consisting of the distribution function, of the Newtonian potential, and of the local density, which is written here. Furthermore. So now, this system has been under investigation for 50 years. And it has been treated by, with respect to many viewpoints. First of all, the most interesting problem in the 60s, 70s until 1990 was the initial value problem. That is, you have a photograph of the star system, so to speak, again in the particle version, and you want to find in which sense can you calculate the evolution of the gravitating system for further times. And the ambition was to find a global existence proof. In local existence, for the initial value problem is elementary now, though you have developed some Grunwald lemmas and so forth and apply them. Let me, because this is almost, I think, the heart of Vlasov-Poisson system, just stress a little bit the difficulties which you encounter when you want to solve the initial value problem for all times. You see, if you give me the equations again. What already Professor Skubachevsky stressed in his talk, just the system.
Press only the point.
Okay.
Do you need this one?
Yeah. You work with Vlasov's equation. But you see that the potential is associated, is linked to the function f itself via Poisson's equation. You see, you have the delta u, and there is the local density, which is the v integral over f. So this is a nonlinear problem because this is linear in f, and there is still the gradient of f with respect to v. And you feel always, when you try to treat the initial value problem, that it is quadratic. And unfortunately, y prime equals to y squared doesn't have global solutions. You meet this everywhere. Of course, then one does the following. One tries to set up a sequence of successive approximations, assuming, using the initial condition, that you know the field in the first place, and then plug in, then you use the method of characteristics to find the solution f0, say, whenever you know u. This is a linear problem, and locally being linear, you iterate, and finally you get a sequence of functions fn, and then try to find a limit. But this limit will not be a global one at first case, because you need certain estimates to, for instance, estimate the Lipschitz condition, which you need to find the solutions of the characteristic systems at any point. So there is a lot of machinery working, but in fact, I myself have worked on this problem and with my group in München, and the entire world, in fact, took place when the solution came up with one of my students, and simultaneously Pierre-Louis Lyons worked on the same problem, and we came up with different answers. This is very interesting. There is a completely different proof from Pierre-Louis Lyons with Pertam and my student Pfaffelmoser, but all estimates relied on things which were done earlier. Okay, so this is, in short, a little bit of information. That is, well, under the specialists, it is said that you have to close the circle by estimating the Lipschitz, or the first derivative. Close the circle. And one doesn't know how the system behaves. There's almost nothing known about t tending to infinity. It can happen that you start out with an initial distribution which has a circle as its support, and the circle goes up. In other words, it develops high velocities, and the high velocities is the point which destroy the global existence, because high velocities means big rho here, And this makes the singularity even worse. This is the singularity of 1 over r squared, of course. But if rho blows up, then you are in trouble. Okay, that's, I think you understand a little bit better what I'm going to do. Further on now, please. Well, stationary solution is our subject today. Stability I will comment on very slightly very later. So we are concerned with stationary solutions today. And I will give you some, I think, equally important measures to find stationary solutions. We omit T in our discussion yet now. And how can we at all find stationary solutions? Well, the first choice is to work with the local energy, which is written here. And then you see directly, without doing much, that E is a solution of Lasov's equation, right? Easy to see. And so, by the chain rule, any function phi of E is also a solution. So, what is now left here? We have this relation. We assume that we work with a given phi, rather arbitrary, and by our equation 3, which is the definition of the local density, you exactly get this form of the local density. Okay, now this is substituting in this definition of h sub phi the running variable u by the potential. Now, the only thing which remains to be solved is now Poisson's equation. Once you have solved Poisson's equation, P1 is now this here, remains to be solved. If you have the solution, then you can define by the definition of E your distribution function just by taking f is equal to phi of EXV. This solves then V. We have already satisfied our third equation, and then U of X solves P1 by construction. So, in other words, resume of that is you can prescribe any function phi of E, and by this procedure you have a stationary solution. A little bit further. In the case of spherical symmetry, this means that your functions which depend on x depend on r, on the radius of x. You have a second integral. And this is the square of angular momentum. So by the same argument which I already presented, any function phi of E and F is a solution. Next page. Let us keep this in mind. There are also in astrophysics more than 2 integrals in certain circumstances, ellipsoidal or coordinates, then you can have a little something more, but I don't want to comment on this. Okay. Second point, we have 3 methods to find stationary solutions, which now evolve from treating the problem of finding stationary solutions. The first is the direct method, which I already more or less explained. You have a given phi of E and F, you solve, you calculate the h phi as before, and then after solving this equation, this is the main part, you define your local density and you arrive at the distribution function f. There are is a theorem which I derived with my students in München, giving you a lot of solutions of this problem. You see, this is in radial symmetry. It is a Poisson's equation to a certain initial condition. And this has been solved also for H which are singular in R equals to 0. I stress this point. I come to this point later. Now, what choices are usually discussed in the literature? Much discussed are the so-called polytopes solutions. They have the form phi EF is equal to E0 minus E, plus means you take the positive part of this function to the power mu times f of k, f to the power k. This, if you write down Poisson's equation, this exactly leans by a substitution to the Embden-Fowler system, which is very much, which was very much under investigation. If you allow here to enter a certain parameter in the representation of phi, you get the Matokuma equation. Matokuma was a Japanese astronomer who set up certain advices to find, to describe stellar systems, and he had several conjectures, which sometimes not all have proven to be correct. But anyway, we now are very well informed about Matokuma equation. Particularly, I wrote a paper, which also I think is worth to mention, because there arises a certain problem. How physical are these solutions? Particularly, which solutions have finite mass and finite radius? This is, of course, I think a good concept to decide whether it's applicable or not. And this has been done for Embden-Fowler, and I did this with Healy in the case of the Matokuma equation. And the main point is the semilinear elliptic equation boils down to a second order differential equation with a linearity on the right side. And by a sophisticated substitution, we managed to bring this in the plane by introducing new coordinates. And what came up was a Lotka-Volterra system, strangely enough. Not with constant coefficients, but one coefficient was varying with time. And then we could apply the theory of Horst Thieme, which is, I think, a student of you. He could characterize non-autonomous systems and the limit sets of them by showing the relation between the limit sets of non-autonomous systems, which are asymptotically autonomous with respect to other systems where you know everything, and therefore this problem of finite radius and finite mass could be solved. You could characterize the finiteness of these things by just looking at their limit sets. Okay, this is, I think I have to be a little. Okay, yet further on. Yeah, this is what I want to say for the direct method. Again, I repeat, the direct method consists of having a phi prefix, choose, find the row. And now we reverse this argument and say what happens if I observe by astronomical observations a certain stellar system, and I know the density. Can I find a phi to this given density? And this is not well understood right now. In the case where I will speak about, it is very, in fact, quite easy, but in this case it's quite complicated. Let me just give a little observation to this point, and not too deeply. So the point is, for later purposes, you have your rho given by u by h, and you have to find the phi. If you go further, next slide.
Check on the screen.
Yes. Yeah, first the case, you have no f. Then you arrive at this equation here, which is in fact an integral equation, and you can reduce this this equation to Abel's integral equation just by differentiating, and so it's more or less Abel's equation, which of course, as you know, has the fs over square root of x minus s under the integral, just by simple reduction. A nice problem arises for somebody who wants to study this question. If you have an f, then this representation of h changes into the more involved right-hand side here. And if you look at this, then you find out that consider this part here on the numerator as momentarily a certain function, say h or what, and then you have Abel's equation, Abel's integral equation with respect to h. You assume you can solve it. Then you know all the integrals from 0 to t over this f which you want to find. And if you look at the plane, then these integrals are all line integrals over the function f which you want to find. And in fact, if you now think of the Radon transform, this is the Radon transform of f, and you know all these line integrals and can hopefully invert it, but it is not so clear because this is a limited angle problem of the Radon transform. This is some work which one could do, which I didn't do, but it would be very interesting to see the applicability of a Radon transform. Okay, now the third, if you lift it a little bit, the third method, which is also very interesting, is to use a variational method to find stationary solutions. I will make it rather short because I have no time. The variation method had been used by Jan Guo, my student Gerhard Rhein, and in cooperation between Jan Guo and Gerhard Rhein, they came up with the sophisticated elaboration of this method. Let me just read to you the statement. Again, in spherical symmetry, the stationary solutions are obtained as minimizers of a certain functional. The functional is written here. What do you have? You have a so-called Casimir functional. This is the following. You choose a decent function q of two variables and integrate with respect to the velocities and the space. So this is, if q is very simple, this is just the L1 norm of f. And because our right-hand side is of the characteristic system has divergence 0, the L1 norm is preserved. So if you, and this is here the energy, the total energy of the system, and you see at once that this functional JF is constant under the flow of the Poisson system. Yeah, this is one thing. So there is to be chosen a class of functions Q with the polytropic solutions between a rather narrow range of powers can serve as a system. It can serve as an example, and the set on which you vary this functional is this set Fm, which consists of integrable functions with spherical symmetry, non-negative of course, with mass m, so the index appears here, and the Jf, the total energy, must be finite. You have an advantage here because the mass m, the finiteness of the mass m, is inbuilt here. You have to ask yourself, is it a solution of finite mass or of infinite mass, as you did before? This is, you will always get solutions of finite mass. So, and you have another big advantage because this serves as a Lyapunov functional for the flow. It is quite easy to clarify the stability of these stationary solutions. So once you have solved this, or you have found a stationary solution by this method, it is more or less automatically stable. Further on, please. Now we are coming to the point. My new message consists of considering a singular version of Vlasov-Poisson system, namely in the following sense. The astronomers observe galaxies, and they found that there are very many galaxies. By the way, our Milky Way is one of these examples for which the width is small in comparison to the other extensions, length and the direction orthogonal to this. For instance, our Milky Way has this ratio 8 to 1. And therefore, well, to describe these star systems, we neglect the width and say it is 0. Mathematically, this means that you are trying to find solutions of Vlasov-Poisson system which are delta distributed with respect to x3, the upper coordinate, and b3. So this is a class of singular solutions which is important in astrophysics. There are many books in astrophysics, for instance, the big volume of Benny Tremaine and Friedman Polyashenko, who deal with this kind of galaxies. So, a new problem. And this new problem raises the question, how do you do the initial value problem for flat systems? My student, Svetlana Dietz, had her dissertation about this, and she came up almost with the same answer, which very well know everybody who worked in kinetic theory. Locally, you have strong solutions. Globally, you have only weak solutions. But he used very sophisticated argument from the topology spaces. By the way, this nice lemma, which was found, I think, when I was in Paris in '85 or so, this Sentis-Goltz-Fertam lemma, which gives you a little bit more regularity when, for the solution of a kinetic equation with a decent regular right side. So she made use of this and came up with this result. And I dared to tell her, well, this is a very nice result, but try to find stationary solutions to make the theory complete. And I was very happy that her dissertation was so big already that she didn't come to this point, because she probably would have failed. It is, it is a problem which I will discuss now, and which kept me busy quite a time. Because you will see Vlasov's equations turn into integral equations automatically. This makes the theory rather rough. But anyway, you will see if I are right or no. So, initial value from is solved, please go further. And then my student Gerhard Rhein, he attacked this problem, flat solutions, in the stationary case, and wrote a work which appeared in 1999, and came up with the existence of flat solutions in the stationary case by the variational method. But the range of existence, if you prescribe phi, was rather small. He used the machinery of condensed compactness and sophisticated functional analytic tools, and I thought one could do more, also with more elementary means. And this is what we finally did. There is a restricted class of solutions for the existence only. Of course, he got also stability, but for existence only, this method did not appear to me appropriate. It should be a more elementary approach to this question. And here begins our investigation. The next slide. So again, our concern is to solve this system. But keep in mind, the potential now is obtained by integration over the R2 and not over the R3. So this makes the singularity really nasty. The singularity is much stronger, and you do not have these nice theorems which you have in potential theory, that if the density is Hölder, then the potential is 2 plus 1 alpha and so forth, you know, all these. And first of all, yes, we now stick solutions. Well, we are very modest now here, and have Q, this is now the old phi, it's now Q, of minus E0 minus E as an ansatz. We are working towards the, or in the spirit of the direct method, to find solutions when phi is prescribed. Note this is minus E0, E0 being positive. Okay, now this is the problem. And to make things a little easier, I change notation here and say V is my minus U. So then you remember how the procedure went. Then you have to find the expression for rho. Lift it a little bit more, please. Thank you very much. Then D gives the following. Look here. D, rho is the V integral over phi. This was the form of phi of this expression. This is V squared. This is the energy, E0 minus the energy. And well, so after some simple integration, you come up with this. And now you define F to be this quantity, Bx replaced by H. This gives you a function F of H. And the, excuse me, I have forgotten to tell you what Q is. Q is a function which is 0 for negative values and is monotonically, strictly monotonic, is important, strictly monotonically increasing on R plus. And so this the integral exists and so forth. And what we get is the following. If you introduce this function f, keep this picture in mind. This is very important for the following. 0 from minus infinity to E0, and from E0 on it starts to be positive. So you get this formula for the local density. It is an integral formula, because V is the integral, as I told you, the integral over R2. It replaces the, if you forget the sign, the U. And if you introduce this operator L, which we have to be with later, this operator L, then you can say the equation here, rho, can be given this form, f of L rho. L rho is nothing else but V. So we have to solve this equation for rho. And to say it once more in explicit terms, we have to solve this nonlinear integral equation of convolution type with a singular kernel. There is no, it is not known, and I don't think it will be true, that our U defined by the integral, as in the 3D case, satisfies any differential equation. This is defined by an integral, and you have to work with this integral equation. But this is the key point. I don't tell you how to come back if you have solved this integral equation, how we come back to the differential system. This is automatic when you have more regularity. Okay, lift it a little bit, please. So we have to solve, let me see, did I once more back again a little bit? Yeah, we must solve D, and we treat the case of spherical symmetry again. Please go on now. We have to study the operator, right? The operator has very few good regularity problems. And this to calculate this integral, even for very simple functions P, is almost impossible. You don't know very much. So what you can do is you can write it as an integral operator, but unfortunately this K, which you get in the kernel, is an elliptic integral of first kind. So very uneasy to handle with. So we did another thing, and we expanded the kernel in a series of Legendre polynomials. I think we can make this, if you go further, please, rather short, because this is more or less standard. Just briefly, do this, and then, of course, 1 over x minus y is expanded in Legendre polynomials, which appear here, Pn, and you integrate and get certain constants an, which are certain integrals over Pn of cosine of theta and so forth. So at least what you do get is a representation of L by infinite sums. How are these constructed? First, there is the descending powers of R, and then the powers of positive, the powers of positive with positive order, and using certain known expressions for the A to L, and using Stirling's formula. Please go a little bit further. Stirling formula. You can see that the constants A to L, which appear here, are very delicate if you sum them up. They are not summable if you don't have a factor which forces them that the sums are really finite. Okay, so this is A to L over L is summable, but A to L is not. Okay, next time. I can, briefly go over the properties of L, which we have to discuss here. In fact, the most easy case is if you have your layer function P to be in L1 intersection L infinity, then you get an operator which maps this space into the space of bounded continuous function on 0 infinity by this estimate. And if P has compact support, you know this from the potential in 3 dimensions, it's 1 over R. If P has compact support. Please go further, please. Yes, thank you. And now we solve the first problem, or excuse me, the second problem. The solution, we find the solution of the inverse problem, as particularly for P's, layer functions, which are strictly decreasing on its support. They have compact support, and they are strictly decreasing on their support. Then the theorem says that there always exists an F, which later determines the Q, such that our equation is satisfied. That is, any such P can be considered as the local density of a flat stellar dynamic model with the triple F, O, U. And I think I have some time to go over the proof. Maybe you lift it a little bit. Important steps in the proof. Go up a little bit. Yes, first step. If P is strictly decreasing on its support, I've drawn you a picture like that here. Then the LP, which I denote now by capital P, is strictly increasing too. Of course, this function doesn't have a compact support. You cannot expect that, never, unless P is 0. But this is the first fact. If you go further a little bit, next slide. The second step is assume this works for P without compact support, but for the time being, I try to show you the proof in a couple of lines. How do we find the F necessary? Lift a little bit, please. No, once more. The picture shows almost everything. If we have the P here, please look from this side. The P coordinate is this here, and the R coordinate goes upwards. So look, please, this here, and then you have your P strictly decreasing with compact support. You have your capital P, and you can invert it, because by the last theorem, there exists P minus 1. And then you compose this strictly decreasing P with the strictly decreasing P minus 1 and call it F. Then the integral equation is satisfied. Well, lift it a little bit. Because if you have P of R, R is between 0 and capital R, then you can, of course, represent P in this form here, because P minus 1 composite with P is the identity. And then, because this here is F, you end up with F composite in P, and capital P just is defined as LRP. So the integral is satisfied, and it's trivial to see that it is for other R. Next. Okay, yes. There is a nice example which is much discussed in the astronomical literature. Oh yeah. This is the Cosmin disk. And well, there you can do the calculations explicitly. We go further. Now we come to the second part, if you give me more, maybe 5 minutes. The direct problem is more difficult.
you have, to make a long story short, you have your f given and want to find r, which satisfies the integral equation. There is no other way, I think, than to approximate p by piecewise linear functions. Here they are. And you are, in the first place, you are satisfied if you can solve this equation just for discrete points. This leads to this equation here, and now you end up with this equation here. G0 is a given function, depending upon a real variable, and you have to find the prescribed partition, and you want to find the AI, which determine your solution. Go on, please. And now the PRI, one line down, please. The PRI are linear combinations of the undetermined AI with coefficients depending on the prescribed partition. And the numerical result is that for any G0 which has the form lambda mu, this is the case which I had before, by numerical means there exists a unique solution. Very shortly now. The problem lies in the fact that you have to calculate the P of Ri for a piecewise linear function. And this leads to long calculations because of the involvedness of this linear operator. Please lift this. I show you one coefficient. It is this form. There come the infinite sums here, which converge and so forth, or these. And this makes the numerical analysis a little bit difficult. Go further, please. So the interesting system is this here, right? A is a constant matrix, and in the right-hand side you have powers of mu. And I had really a hard time to solve this system. Nothing works. No fixed point theory, no degree theory. And later I found that you have to take the quotients of the unknown variables and have, can you reduce at least for n equals 3 the order of the system, and end up with these two equations. And how to solve these? I did the following. Q and, look at this system here. Q and Q bar determine certain surfaces in the space. And you want to satisfy this equation and that equation. What you do is you consider the contours, the curves of equal height for this and that. And there you can represent B and beta, the unknown, B, beta and lambda by age, by the height, and do the same for this, and try to see where these vectors meet in the R2, particularly in the R2 plus, very shortly. And this is the first, what we have here as a function of age. We have here the first component. You see how involved it is, and it's getting more and more involved the smaller the mu is. So high values of mu are okay, but then you have exactly one solution, but you have 7 solutions if you come down to mu equal to 1 over 21. And you want to have a decreasing sequence of solutions. This is another thing. And there a miracle happens. Namely, for any mu positive, there exists exactly one decreasing function. And you can have many more of very difficult and involved size. But for in a certain triangle which you are looking for, there's only one solution which is physically relevant. Okay, I think we have more or less done said everything. Thank you very much. I wanted to give some open problems. Now we can do this personally. There are let me just make it short. First of all, extend this. Yeah, okay. Thank
you. Unfortunately, we have no time for discussion. Maybe some short question. Only one, please.
Okay.
Please, one question.
Question and comment. First, to be sure, here you are dealing with stellar atmosphere, which means that the energy, the potential energy, has a negative sign.
Yes. Yes.
Just to say,
yes.
To introduce my talk,
yes.
I will
yes.
talk about things where it has a positive sign.
Yes. Yes.
But then I have a question about that. Do you have any idea about the existence of stationary solution in the whole space with finite energy for the positive sign, for the other sign? Do you know if they exist, or is there a simple argument?
Case, right, with the inverse sign in Poisson's equation, or
to say that they do not exist finite energy, or they do? When you have the other sign.
You mean the -1 in Poisson's equation?
Yeah.
Yeah. You are talking about the plasma physical case, right?
I'm talking about the stationary
or astrophysical.
With the potential energy with the other sign.
I mean, by conservation of, for instance, if you look at the variational method,
there should not be a finite energy.
Works from the very beginning with a finite energy. And if the two components of the energy, the kinetic energy and the potential energy, have both the same sign, boundedness of the energy means boundedness of every term. Is this what you mean? Probably not.
No, I'm wondering if there exists solution of finite energy.
Yes. Yeah.
So we have to stop at this point to send again to the speaker. Without break, we have to continue. Next speaker, Professor Veron.
Thank you very much.
The talk is line-ended question with measures.
So how do I move the system?
Yes, are you familiar with this? So this one means next slide, this one is previous
okay.
slide, and this one is the pointer.
Okay, that's good. So I start? I start, yes. Okay. There is a break?
Oh.
Okay. You have an announcement, so what? We start, okay.
You have additional 5 minutes.
Okay, that's good, thank you. Okay, so, well, I'm great pleasure for being here. I think it's maybe 6th or 4th time I'm coming in for these meetings, and maybe if I add all the Petrovsky meetings in which I took part, I think it makes many, many meetings. And okay, I would like to also to dedicate this this talk to the memory of somebody who was a very good friend and a wonderful person, Stanislav Porožajev. And this picture was taken in Haifa in 2011. He came at the occasion. There was a conference organized for my wife and me 60th birthday, and he took, and this was taken during an excursion. He was a very great man. Okay, so now I'm going to present my talk, and I have a few notations before, and I am interested. You say I consider omega to be a bounded domain with C2 boundary. and G is a Cartesian function which is non-decreasing in the second variable. And for simplicity, I shall assume at the moment that G of x and 0 is 0. And I'm interested in look to this type of equation here, with a quasi-linear equation with so this monotone absorption term, and here with the right-hand side is a measure. Here delta P is the classical P Laplace operator, and mu is a bounded measure. And the two cases I will consider essentially that G of x and u is x to some minus beta u to the q minus 1 times u. And G of x and u is sine of u times exponential of tau, absolute value of u to the lambda minus 1. And usually I'm interested in the case where this is the growth of the nonlinear term is bigger than the growth of the homogeneous term, because of course it's not linear, and that means that usually q will be bigger than p minus 1. I'm going to give you a few notation which may be a little boring, but I think it's needed because it's a framework of the system. So this is a space of MB is a space of bounded random measure in omega, and with a plus is a positive. And now the work will be done with this type with a Lorentz space, which is a kind of extension of sharp extension of Lebesgue space. It gives a sharper scale of space, which they are defined classically. If you look at the f star is a decreasing rearrangement of a function f. F double star is the average of the decreasing rearrangement. Then you define the F LSQ, the norm of F in the Lorentz space LSQ, with S in SQ in this range, by this expression here, okay, and by this expression here when Q is infinity. Roughly speaking, LSQ can be also defined by this expression. It's not exactly, this is not a norm, but it's a quasi-norm. And remember also that LQQ is a classical space, a classical Lebesgue space. So it is just a sharper form of Lebesgue space. Now, again, the regularity, all this type of problem, we need to introduce the Bessel kernel. The Bessel kernel G alpha is the inverse, the Fourier inverse of 1 plus x squared to the minus alpha 2 over 2, okay? This is the inverse function in the space of S prime. And now the Bessel Lorentz space, potential space, is defined is a set of functions f which are a convolution of G alpha with a function little g belonging to LSQ. Okay? So again, and for this, you have this space, and you define the norm of this. Is as extension, if you want. This R can be extension, of course, of Sobolev spaces, and with a little sharper estimate. And alpha is essentially the half of the order of differentiation. Okay, and now the norm of F in L alpha SQ is a norm of G in LSQ. Okay, and this can be defined like this. Now, with this space. Also, we defined a system of capacity, and the capacity is defined classically. The capacity of a compact set is the infimum of the norm of phi in L alpha SQ, with phi is a function with a rapidly decreasing function, which is bigger or equal to 1 in neighborhood of k, when k is compact. And then you extend, of course, classically, this capacity on open set and then on any set. Okay, this is just introduction. And now I'm going to recall a little the problem when p equal 2, because when p equal 2 it has a long story. We look at I don't know if you or me, it's okay. Okay, it has a long to move it maybe a little, no, I don't know if you hear it very well.
You can hold it. It's not fixed.
Oh, that's better. Okay, so now I take the problem is equal to with just G is continuous, non-decreasing for simplicity with vanishing at 0. And starting case is a result of the theory which was developed by Brezis and Benilan. And Benilan proved the following, that if assumes that G satisfies the integral of 1 to infinity of G of S plus G of minus, absolute value of G of minus S times S to the minus 2 n minus 1 over n minus 2 ds is finite, then there exists a solution of this equation, a weak solution of this equation for any bounded measure. And if G of u is uq minus 1u, this means that this condition here means that Q is subcritical. So what is this terrible condition? It simply says that G of the Newtonian potential of R to the 2 minus n is integrable on the ball B1. This is just this meaning. So, and then after you change this form. Now, when you go, this is so the class, this is for solving for any measure. Now, if we want to solve for any Q, you have to add condition on the measure. You have to add condition on the measure. In some sense, these are the result of Barras and Pierre in 1984. The measure cannot be too concentrated. The measure cannot be too concentrated if we want to solve it for any Q. And in particular, of course, this is for Q is bigger than Q, the bigger or equal to this critical value, n over n minus 2. But this is contained, everything is contained in this theorem. So if you want to solve this equation with a bounded measure, okay, you can solve it if and only if the absolute value of mu is absolutely continuous with respect to the Bessel capacity C2Q or Sobolev capacity C2Q prime, which in the Bessel-Lorentz framework says C2 Q prime Q prime and is associated to the Sobolev space W2 Q prime. Q prime is Q over Q minus 1, so the absolute continuity means that the measure vanishes on set with C2 Q prime capacity 0, on Borel set with C2 Q prime capacity. So just look for simple fact, which will be important. For P equal to, we use a green potential, the green kernel, G of X and Y. And to this green kernel, we associate the corresponding green potential of a measure. So if we have a solution of equation 2.1, which is minus Laplacian of u plus G of u is mu, then a weak solution, then u is in L1, G of u is in L1 rho, rho is the distance to boundary, and this solution u mu is expressed by this form. That means u mu is G of mu minus G, capital G, this is green potential of the nonlinear term G of u mu of X. You have a weak formulation, which is actually the good one. The weak formulation is a formal, it's just a formal integration. You just multiply by a test function and you do it formally using the fact that this test function vanishes on the boundary. Okay, of course, you have not the right to do this if mu is just a measure, so you take this as a definition of the weak formulation, that for any function zeta, which is in W1 infinity 0 intersect with W2 infinity, actually you can a little weaken this condition. Which is important is just to have that the Laplacian of zeta is in L infinity. Then this expresses that minus integral of minus u Laplacian zeta plus G of u zeta is integral of zeta d mu. You can notice that everything has a meaning because u is in L1, Laplacian zeta in L infinity. Now if zeta vanishes on the boundary as in W1 infinity, so zeta is going bounded by C times rho. So if G of u is in L1 rho, this is integrable. So it gives us a sense of all the things, it is something natural. And with this formulation, we have essentially existence and uniqueness. So that means that it's a good shape. And of course, if mu is more regular, so you have more regularity. I'm going to give first an outline of the proof of Benilon-Bresis, because we shall use this outline to extend after that to quasi-linear equation. First observation, if mu is positive and g of u vanishes, you take a function, a series of approximation of the measure by this infinity function, which converges to mu n converges to mu weakly. Of course, you can solve the problem with this right-hand side mu n, strong solution, and you call it u mu n. So what you have, okay, here, you here. Okay, so you first thing that the equation, since mu n is positive, the equation solution of the equation with absorption is smaller than the g of mu n. So the consequence is that since g is increasing, that g of u mu n is smaller than g of capital G of mu n. Now, when you have the weak formulation and you take as a test function, I call it zeta g of 1. What does it mean? It means this is minus Laplacian of eta is 1 and eta vanishes at the boundary. And this is a good test function. You take it, and then you have this expression here. Integral of u mu n plus eta g of u mu n dx is integral over omega of eta mu n. Now this is bounded because the measures are weakly convergent. And the consequence that here everything is positive, so you have a priori bound. You have a priori bound of u mu n in L1 and of g of u mu n in L1 rho, because eta behaves like c times rho at the boundary because of Hopf lemma. Now, because of a priori estimate, you have the u mu n goes to u in L1 and almost everywhere. This is just a regularity theory of elliptic equation with in L1. Since g is continuous, you have g of u mu n k goes to g of u almost everywhere. So the main problem now is to go to the limit in L1 for the g of u mu n, because we want to go to the limit in the weak formulation. Okay? Second observation, you look, since u mu n is less than g of u mu n, the measure of the set where u mu n of x is bigger than lambda is smaller than the measure of this set here, of the set where the green potential of the measure is bigger than lambda. Now, for this, you can express, you know, everything about this set here. This is very simple, that this set, the measure of this set is smaller than c times lambda to the minus 2 over n. This means that essentially you have an estimate g of the green potential of a measure, a bounded measure, belongs to the space L, the Lorentz space L, n minus 2 infinity, which is also called the Marcinkiewicz space n over n2. So you have the same, of course, with u. Now, how to go to the limit when, how to prove that g of u mu n goes to g of u? Well, for most of this type of problem, since we have a uniform bound in L1, we have the convergence almost everywhere, we go to the limit using Vitali theorem of uniform integrability. So you take a Borel set, you look at the integral of g of u mu n on this Borel set, you say that this is equal where u mu n is less than lambda, plus in the same term where u mu n is bigger than lambda. The first term, you dominate it because g is increasing by g of lambda times the measure of E. And the second time, you integrate just using this measure, but still just integral. You just say that this is minus integral from lambda to infinity of g of s, d of this measure, the measure of this set here. Integration by part, still just integral, says that this is dominated by g of lambda times the measure of E times c times integral from lambda to infinity of this. So remember, this is exactly the condition of integrability at the infinity. Now, if you want to make this smaller than epsilon, so first you fix lambda such that it is smaller than epsilon over 2. And then after that, you take the measure of E, so that this term also is smaller than epsilon over 2. Also, you have this. You have the uniform integrability, and you can go to the limit. After that, this technique has been extended to boundary measures. Then for measure like rho to the alpha, for alpha between 0 and 1, that is a weighted measure. And of course, after that, I have a general extension. And everything of this type of extension is gathered in the book I've written with Marcus in the Greater series, which appear in 2013. So this is the subcritical case. Now the supercritical case. Also other observation of Barras and Pierre. First, an object that if you assume that you have a positive measure, such that the G, the nonlinearity G of the potential of the green potential of the measure, it belongs to the space L1 rho, then you have a solution U mu. Why? Because essentially the green potential is the green potential of mu is a super solution. So if G of the green potential is in L1 rho, you have a good super solution and you can construct a solution. So this is first observation. Second observation, if mu is positive and if you have the green potential of the measure belongs to LQ, it means a regularity on the measure. That means you solve an equation. It says that the measure belongs to the Sobolev space, the negative Sobolev space W minus 2Q. Intersect with positive measure, of course, because we assume this. Now, if you take a positive measure, and if you have a solution, then you take a test function, positive test function, and you have, just by using Hölder inequality, integral of omega over omega of zeta d mu is bounded by this term, times integral of u q zeta to the 1 over q, times integral of zeta minus q prime over q times Laplacian of zeta to the q prime over 1 over q prime. Of course, this can be infinite, of course. Now, but if you have a compact set, we see two q prime capacities. The Sobolev's capacity is 0. Then there exists a sequence of C-infinity functions which are between 0 and 1, bigger or equal to 1 neighborhood of k, and which goes to for which the Sobolev norm W2Q prime goes to 0. And now if you take zeta n, this type of object, eta n to the q prime, so this is a good test function, and for this you put it inside and you compute, you see that this term here goes to 0. Now, of course, if the capacity is 0, if this goes to 0, it goes also to 0 almost everywhere. So it means that this goes to 0. So since zeta is bigger or equal to 1 on k, this implies that this is 0, and this implies that integral, the mu of k, which is less than integral of zeta d mu, is 0. So if you have a solution, then the measure must vanish on set with C2Q prime capacity 0. For the this is another observation. Other observation, if you have a positive, a sequence, an increasing sequence of measure belonging to the good space W minus 2Q, intersect positive measure, which is increasing. And if it converges in a weak sense to a measure, then the corresponding problem 2, 3, that means minus Laplacian of u plus uq equal mu. This is my problem 2.3. If I have it here, yes, this problem, okay, then it can be solved at the limit. Increasing limit of admissible measure is an admissible measure. And the finite step for proving all these results, if you have now, and this is important because we know that it is the fact that the measure vanishes on set with a capacity 0 is a necessary condition. Now, if you have a sequence, if you have a measure which is absolutely continuous with respect to this capacity, and this is a general result actually, then there exists a sequence of, an increasing sequence of measure belonging to the good space, minus w minus 2q intersect with mu plus, which converge to mu in the weak sense. Okay? And you can write this measure in this form. Mu can be written as an L1 function plus this part. This part, remember, that means that G, the green potential of mu belongs to LQ, and for which we know that we can prove the result. Okay, this result is something which is rather deep. It was used, there was a separate proof by Fayel de la Pradelle on one side and Dalmazo on the other side using Hahn-Banach theorem. But actually, I learned 3 months ago that there was a previous proof due to Mokobotsky, which appear in notre compte rendu. Now I go to the quasi-linear framework. So now I'm interested in minus delta P of u plus G of x and u is mu. Decomposition of measure. So if you have, this is a general valid for essentially for any type of capacity. If you have a bounded measure, then you can decompose this bounded measure in 3 parts, in a sum of 3 elements. As a first part, you have bounded measure and you are given a capacity. C alpha SQ, I take a Lorentz, a Bessel-Lorentz capacity because I'm interested in this type. So this measure can be decomposed at a part which is absolutely continuous with respect to these capacities, that means which vanishes on set with C alpha SQ is 0, plus 2 singular measures respect to this, this capacity, that means this mu plus, which is positive, and mu plus and u minus are positive, and you assume that, and in that case, mu plus and u minus have support in set with 0 capacity. Okay? This is a general decomposition of measure, and also you can also define what's called the gradient almost everywhere. These are the ingredients we need to define the solution of this quasi-linear equation for the P Laplace. If you have a Borel function, which is finite almost everywhere, and if you assume that the truncated of this function belongs to W1 infinity for any k, Tk is just the truncation of the value which respects the sign. Okay. Then you define the gradient almost everywhere by gradient of u is y, okay, by just the fact that the grad of Tk of u, which exists, is just y times the characteristic function of the set where absolute value of u is less or equal to k. So you can just define this value almost. So these are the ingredients. And now this difficult notion, which is how to define now a solution of this equation. So after I think a long research, the people went to the definition of renormalized solution. I think the definition of renormalized solution can be attributed to Lyons and Murat, if I'm correct, although there are some other people claiming that they have it before, but okay, so this is a natural phenomenon. So you take a measure. You take a measure and a Karateoderi function. And you want to define, this is interested in defining the solution of my equation is minus delta P of u plus G of xu is mu. Okay, what do you say by, what is a renormalized solution? U is a function which is defined in omega. Okay, you assume that G it's measurable and finite almost everywhere. G of u is, you assume that G of u is in L1. Well, this cannot be avoided. And also, you assume that the truncation Tk of u is in W1p for all k positive. P is the P of the P Laplace. Now something which is a little strange, but is needed in the proof, and it is normal, we find it naturally, that the gradient almost everywhere here, grad u to the p minus 1. P minus 1 can be, is positive, but it can be less than 1. This is one of the difficulty. So assume in that case, this is for a renormalized solution, it is assumed that it belongs to LR for R between 1 and n over minus 1. Now about the test function. Test functions also are not easy. You know that for any h which is W1 infinity with h prime as compact support, that means the function h become constant for the variable large enough. And any function phi in W1m for some m bigger than n, such that h of u phi is in W1p0, okay? You have this expression. So this expression is just, so this contains a truncation in some sense. This is the notion h of u is equal to constant if u is too large, because h prime has compact support. So this is a truncation in some sense. Integral over omega of grad u to the p minus 2 grad u, grad of h of u phi, plus g of x of u, h of u phi dx, okay, is equal to what? Now is equal to h of u phi d mu 0. Mu 0 is an absolutely continuous part with respect to the C1p capacity. So you can define this object because h of u phi belongs to W1p. So if the measure mu 0, this is the absolutely continuous part, is absolutely continuous part, continuous respect to this capacity, so you know that in that case, h of u phi admits a quasi-continuous representant, so that this has a meaning. Now, the mu plus and mu minus are the singular part, respect always to this capacity, and okay, and this is equal to this, the regular part plus this part. So what's the meaning h of infinity times integral of phi d mu s minus h of minus infinity integral of phi d mu s? So what does it contain? It contains the idea that if there is a singular part, remember this is roughly h of u, so if there is a singular part, u is in some sense infinite. So this is the infinite part of this which is contained. And you take out because function is constant. So you take this part. So this is the idea. So this definition of renormalization, of renormalized solution, and the main progress about renormalized solution are due to Dalmaso, Mura, Orsina, and Prignier. I think in 1999 they published a very, very important and deep paper where they proved two types of stability result. Two types of stability result for renormalized solution. Also notice that there are several equivalent definitions of renormalized solutions. Some of them are easier to handle. It depends what we want to do. So the first result, in some sense, this is an easier one. If you take a sequence of, you consider a bounded measure, which are uniformly bounded, okay? And now you look at the sequence of solution, renormalized solution of minus delta p of un is mu n, which vanishing on the boundary. Then you can extract, okay, notice there is no uniqueness known for this type of problem. The uniqueness is completely, is almost completely unknown, except mu is a Dirac mass, or a sum of Dirac mass, and these are all result of Kishinesami and myself. And now, if from this you can extract a subsequence of the mu n and the un, such that first, of course, the mu n converges weakly to mu, this is because of this, and the unl goes to u almost everywhere, where u is a solution, not a renormalized, just is a solution of, in the sense of distribution of this equation here, such that the supremum of 1 over k, the gradient of tk of un is bounded for some fixed n, for all k, but m is not independent of k, of course. Now the second theorem is this one, which is the most important one. It is a sharpening It's a sharpening effect of the decomposition of measure. Now I go to the decomposition of measure using the C1p capacity. So mu is mu 0 plus mu s plus minus mu s minus 1. S minus. Okay, now mu 0 is a regular part with respect to the C1p capacity. You can write it as a sum of an L1 function and the divergence of a function of a vector which belongs to Lp prime to the n. Okay, so you write mu 0 in this form. Now these are the singular part with respect to this C1p capacity. Now you assume that there exists a sequence Fn in L1 and Gn in Lp prime to the n. And a sequence also of eta ng, G is 1 or 2, okay, in bounded measure, such that first Fn goes to F weakly, Gn goes to F strongly in Lp prime, and the divergence here of the Gn is bounded in the set of measure. And now the eta n1 goes to mu plus s, and eta n2 goes to mu minus s. In the narrow topology, this is a slightly larger topology than the usual one. The narrow topology, that means you take test function which belongs to C of omega intersect with infinity, which are bounded continuous functions. Now, if you look at a solution, un is a renormalized solution of this equation, minus delta p of un equal fn minus divergence of gn plus eta n1 minus eta n2, vanishing on the boundary. Then you can extract a subsequence of this un, which converges almost everywhere to a renormalized solution u of the same equation here. And furthermore, you have the convergence of the truncate of u in W1P0 for all k. So many now, because of this, it looks as a complicated, of course, theorem, but in order to solve problem with boundary, with right-hand side measures, the problem will be always to try to decompose the measure into this form, because this is the only stability, essentially the only stability result which is known for renormalized solution. Now I go to the power case, first the simple power case, minus delta p of u plus uq minus when u is mu in omega, and vanishing on boundary. So the subcritical case was treated by Marie-Françoise Bidault-Véran in 2003. There is a critical exponent for this problem, which is np minus 1 over n minus p. And if you take a bounded measure, and you assume that p minus 1 is less than q is less than qc, then there exists this problem admits a renormalized solution. Okay? Now, there are some partial result in the supercritical case, and this is actually the most important part of my talk will be devoted to this. In the supercritical case, and okay, you have this observation that if there is a solution of this equation, then for any epsilon positive, you can prove that mu is absolutely continuous with respect to this capacity, which is a Sobolev capacity, C1 PQ, Q plus 1 minus P plus epsilon. That means essentially we have an order of differentiation which is equal to 1. And this is the power. It's important to remember this type of, this coefficient here. And in the same way, there is also a removable a theorem of removability. She proved a theorem of removability. You take a compact set with C1 PQ, Q plus 1 minus P plus epsilon capacity is 0. If you have a measure which vanishes on K, okay, and if you have a renormalized, U is a renormalized solution of the equation minus delta PU plus UQ minus 1 U in equal mu in omega minus K, then you can extend it as a solution in the whole set omega. In some sense, means that a set with the capacity, this capacity 0, is removable. But what is important also first observation that if C1 PQ over Q plus 1 minus P plus epsilon of K is 0, and if Q is subcritical, then K is empty. So that means that it contains the result we know. It contains the classical, the subcritical result. It's empty because of Sobolev embedding. Very simple. Now, our second observation also, that how this type of result were proved, essentially, just by taking good test function, and you have essentially minus, you have essentially integral of grad u to the p minus 2, grad u, grad zeta, for good zeta. And whatever are all the manipulation you can do, you can essentially handle with C1 capacity, C1R capacity. You cannot hope to have a stronger capacity. Okay, this is so you can improve the gradient estimate, you can improve things like that, but you cannot go further than C1 capacity. Okay, also notice that the result with with L1 data is due to Bocardo, Galouet, and Vasquez. Now I go to the how to deal now with the supercritical case. And the supercritical case is using a tool which is completely different, which is called the Wolf potential. So what are Wolf potential? Wolf potential, you take alpha is positive, p is bigger than 1, you assume that alpha p is less than n. And the Wolf potential of a measure, of a positive measure, is just integral from 0 to infinity of the mu of bt of x. This is a ball of center x and radius t, divided by t to the n minus alpha p to the 1 over p minus 1 dt over t. And if, in many cases, your measure have support compact support, or you are working with a bounded domain, so it's natural to introduce R truncated potential. That means you just integral between 0 and R at the same form. So this is analogous. For p equal to, you find exactly the Ritz potential, this classical Ritz potential. And the Wolf potential are extremely useful to give representation of solution of minus delta p of p is mu. So now the result I'm going to quote are results which are due to Marie-Françoise Bidot-Véron, Hung, Nguyen, Koch, and myself, and it has just appeared in the Journal of Math Pure et Appliqué. The first observation, remember that I've said that when you have the green potential of a measure is in LQ, it means that the measure belongs to W minus 2Q. Okay, you have a similar form. If the Wolf potential of a measure belongs to a Lorentz space LQS, then the Bessel potential with power alpha p of this measure belongs to the space L, the Lorentz space LQ over p minus 1s. So this is the first result, that you take alpha positive, p is 0 is less than p minus 1 less than q, and always alpha p less than n, s between 0 and infinity. For any R positives, you have a constant c, such that for any positive measure, you have this estimate. That means equivalent of the Wolf potential in LQS and the Bessel potential of the measure in the space LQ over p minus 1s to the 1 over p minus 1. And okay, this type of result is, I think it was a difficult result because you use a lot of potential theory. You have to use essentially a Whitney decomposition of the space, and this is a very delicate proof. Similar thing can be found in the book of Stein, but not this one. The second estimate that essentially the Wolf potential may represent, as the idea that we represent the measure. So there is I think the link of Wolf potential with positive superharmonic function is due to Kippelainen and Mali. I think it appears in the 90s. And they obtain estimate for positive p superharmonic function. And we extended this result, essentially saying that the Wolf potential represents completely a renormalized solution of minus delta p of u is mu. That means you assume that omega is a bounded domain in Rn. Then there exists a constant c, positive, which depends on np, and such that for any mu bounded measure, and u a renormalized solution of the equation minus delta p of u is mu, you have this estimate that u is bounded from above by c times the Wolf potential, okay, truncated to the twice the diameter of omega of mu plus, and bounded from below by minus c times the Wolf potential of the negative part of the measure. So this is a precise estimate of the solution. Now, I would like to link now the technique how to use this, how to solve equations. So you can say, well, remember the fact that we have the green potential of a measure is it belongs to some space, Marcinkiewicz space, plays a very important role, and this can be estimated. It was estimated in saying that the measure of the set where g of mu is bigger than lambda is smaller than lambda to the minus 2 of n. Now assume that you have the following for a measure. Assume that for a measure you have the measure of the set where the Wolf potential of mu plus or minus is bigger than lambda. The measure of the set is bounded by c lambda to the minus q. Okay, this implies, because of this estimate, that the little theta of lambda, which is the measure of the set where capital U is bigger than lambda, is also bounded by c2 times lambda to the minus q. Now, but this estimate here is an estimate of it is an estimate in the space. I tell you, it's an estimate in the Lorentz space LQ prime infinity, or the Marcinkiewicz space LQ prime infinity. So this is equivalent, because of our equivalence theorem, of an estimate of the Bessel potential of the Bessel potential of order p of the measure in this Lorentz space L q prime over p minus 1 infinity. And okay, now we know that the Bessel potential are acting very nicely between Sobolev space, Lorentz space. Exactly, they realize very good isomorphism between this space. So this is essentially means that we have, if this is in this space, it means that the measure mu plus or minus belongs to the space L minus p q prime p minus 1 infinity. By this is the theory of Bessel potential. But what is this space here? L minus p q prime p infinity. It is just a dual space of LP q over q plus 1 minus p1. And the measure which belongs to this space here is absolutely continuous with respect to this Bessel-Lorentz capacity. Now, how to use now the technique of the Vitali theorem. Second observation, that if G is increasing and satisfies this estimate, assume that you have an increasing function satisfying this estimate, you have a sequence of bounded measures which are uniformly bounded in this space here. And then in that case, that means that the corresponding solution UN are uniformly bounded, and they satisfy this here. We have this estimate here. And so you can go also to this one. Then the consequence is that the sequence of G of UN is uniformly integrable. This is exactly the same construction as the one of the first. G of UN is uniformly integrable in L1. So you can go to the limit. You know, remember that all the difficulties is always to go to the limit in the nonlinear term. When you have a solution in approximation, even with minus delta p of un plus g of un is mu, you have an approximation. The difficulty is to go to the limit in this case. And so this allows to go to the limit in this term. Okay? And now I can state with this, the theorem, if you consider this type of solution, the theorem is the following. Take p between 1 and n, q is bigger than p minus 1, and beta is between 0 and n. G is continuous, non-decreasing, and satisfy this condition for 6, that means integral from g of ss to the minus 1 minus q ds is finite. Then if you have a measure which is absolutely continuous with respect to this capacity, so this now you have a capacity which has an order of differentiation in some sense equal to p, not to 1. This is a big difference because there is not we do not use integration by parts, the integration by part formula. So if you have a measure which is absolutely continuous with respect to this capacity, then you have a renormalized solution of this equation, and furthermore, it satisfies this type of form. Okay, and this result extends, and now I can just tell you what happened. I think it's my time is going to be over. Yes, okay. Just to tell you, in the case of the power, of course, you have also an extension of result of Barras and Pierre for power. If you look at this, okay, we have added this for fun. Minus delta p of u plus x to the minus beta u q minus 1 u is mu. And if you have a solution, a measure which is absolutely continuous with respect to this capacity, so this is a, you see here, we have an improvement of this capacity because it's a power. And so you can solve the problem. You have a renormalized solution of this equation here. You have there exists a renormalized solution of this equation, and the solution can be estimated by the Wolf potential. Okay, so just to say one word, in the case of, if you want to go not to power function, but to exponential function, so the Wolf potential have to be replaced by maximal operator, the maximal operator of a measure, which is defined there, and which are also equivalent. You can estimate the maximal operator of a measure by respect to some, again, the same proof, type of proof, by the Bessel potential of this measure. And as soon as you have this, then you have this type of result. And this is the end that you look at this equation here. So it's an exponential. Okay, you decompose your measure in this form. Mu is mu plus minus mu minus. Mu plus is L1, a part which is in L1, plus a perturbation which has the maximal potential, maximal operator bounded. Then you have a solution of this equation. Okay, I'm going to stop there.
Please, questions?
May I ask you, on one place, in the simpler situation, you were talking about uniqueness, which you said you can do for delta as measured,
Yes.
and not for general
Yes.
mu. I'm astonished, sorry.
Okay, I'll tell you why. At that time, it was that's a result I proved with Krishnasamy in 1984. At that time, we didn't know anything about renormalized solution because they do not exist. But we use the following fact. If you have there is an old result from Jim Serin from 1964, saying if you have a solution of minus delta p of u is essentially is 0 outside a point, and u is bounded from below. So you have two possibilities. Either u is bounded, the singularity is removable, or u is essentially estimated by the up to two constant positive, and say that u is bounded from above and from below by c times the fundamental solution corresponding to the P Laplace. Okay? So this was first observation of Jim Serin. Then with Krishnasamy, we proved that actually in this case, we have that u behaves exactly like c times some this fundamental solution for some C, which is linked to the mass, to some direct mass, because there is a direct mass. Okay? And now if you have two solutions which behave like, exactly like the same type of behavior, because of maximum principle, you multiply one by 1 plus epsilon, you have a super solution, and it's going to be bigger than the other one. And you can reverse. So in the case of direct mass, which are bounded from below, we know the result because of that, because of the same singular behavior. Okay? And after that, any renormalized solution of a solution with a minus delta P of u with direct mass is positive. So that's the result. We have the result for solution with direct mass. But the link is only because we know the precise behavior. And we can play with multiplying by 1 plus epsilon and then using maximum principle.
But if you would have general, if you would have some kinds of other, some measure of other, you have results where you have multiplicity.
No, we do not have. If we have a precise behavior, we can do. But you cannot make the difference because it's not.
Yes, it's clear, but
that's a big problem. In L1, it works. In L1, this is the theory of which has been proved by who? There were many. Benilan, I think there was Benilan, who's that? Gary P, Pierre, Vasquez. Did I forget somebody? Bocardo. Okay. There were 5 or 6 to prove it. They prove it in L1. In L1 using, but in the measure, except for direct mass or sum of direct mass, finite sum of direct mass, the problem remains completely open. Okay, so parabolic is on the way, and there is actually a series. Okay, there is an adaptation of this technique of renormalized solution with a same stability lemma theorem actually, which is going to be proved by Marie-Françoise and Ung. Ung is our Vietnamese student. He's absolutely genius, so it's clear that he helped us. And so this is something which supposed to be appeared, I think it is formed in the Journal of European Mathematical Society with many applications. So there is a similar stability, but it is much more complicated because of the T derivative. This is a story which makes the thing much more difficult. So it's, but you know, okay, up to now, renormalized solutions are a tool. Maybe people could think that it is not completely satisfactory, but we don't know how to do without them. There are several other definitions which are maybe simpler and of solution, but it's something which is heavy, but we don't know how to do without it.
Please, some comments?
The last one.
Then we have to send. Well, 10. 20 minutes. Не, ну так.
give opportunity to speak Catherine Pendel from University of Basel. She will give a talk about similar elliptic equations in space of constant curvature. Please.
So I'm very glad to be here and very honored to participate at this conference. And I would like to thank the organizer for giving me this opportunity to be here. Thank you very much. So today I would like to report on some equation of the following type. Laplacian u plus lambda u plus u to the p equals 0 in some domain in Rn. We are looking for positive solutions, and for simplicity, I will, in general, assume that this domain is a ball, because many special features of this equation are visible already in this simple case. And we consider Dirichlet boundary conditions, and we assume that p is bigger than 1 and lambda is just a real number. We have seen this equation in the, oh no, we haven't seen, but this equation appears in the models of stars. It has been derived first by Emden for describing the growth of a star, and that appears also in some models for galaxies. And has been the analysis, the mathematical analysis of it has been started with a work of Fowler, and therefore it's often called the Emden-Fowler equation. So what are the necessary conditions for solutions? As I said, we are looking for positive solution, so lambda has to be smaller than the first eigenvalue of the membrane problem by the maximum principle. And we can also use the Porsche identity, which is written here. So minus r is the radius of the star times the boundary integral over u squared is equal to this integral here. And we see immediately if the left-hand side is always negative, and if the right-hand side is positive, then there are no solutions. What does it mean? This means there doesn't exist solutions if p is bigger than this exponent, which will play an important role in the whole discussion of such problems. And if lambda is smaller or equal to 0, or if p is equal to this critical exponent and lambda is strictly negative. The Porsche identity holds also can be derived for arbitrary domain, and there we get the same result for domains which are star-shaped. And this was really a very important observation which was made by Porsche, as we know, and which leads to many important non-existence results. Maybe I should mention that such an identity was also found by Rellich. He applied it to the linear problem, so if just to the eigenvalue problem, but he couldn't get any conclusion out of it. So I really think that it's correct to call it Porsche identity, because he really made could deduce important facts from it. Now, the existence, if P lies between 1 and this critical exponent, and if lambda is smaller than lambda 1, then one can show that there exists a positive and solution, and it is unique. The method to prove existence, there are several methods, but probably the classical method is to look at the variational problem of this type, and to show that because we are below the critical Sobolev exponent, P plus 1 is just a critical Sobolev exponent, so we can apply the direct method of calculus of variations and show that there exists a minimizer, and this minimizer is up to the constant factor which can be scaled out. It's a solution to the equation. And the uniqueness is maybe less classical. The uniqueness follows first from the moving plane method, which says that every positive solution in a ball of this type of equation must be radial. And then there is a very nice paper by Men Kem Kwong and Yi Li for uniqueness properties of rather general ordinary differential equations, and this criteria they apply also to our equation. I should mention that the existence proof works also for general domains. There is no need to assume that we have a ball, but the uniqueness proof doesn't. I'm not sure that in general uniqueness has been established for general domains, so it's still an open question. Now the interesting case is when P is the critical exponent n plus 2 over n minus 2. And this problem comes up in geometry, because the equation is invariant under Möbius transformations, and it has been considered and studied first by Yamabe, but in the whole domain and not in a bounded, not in the ball with a boundary condition, and so it has been extensively studied by geometers. And the case we are interested in the ball with Dirichlet boundary conditions has been studied by Bresis and Nierenberg in a very nice paper. They showed, you remember, if lambda is negative, then there are no solutions by Porsche. And oops. They showed that if lambda is between 0 and lambda 1, the first eigenvalue problem of the linear problem, then there exists a unique positive solution in the ball. And if in 3 dimensions, if n equals 3, such a solution exists only in an interval, positive interland, which is between lambda 1 over 4 and lambda 1. They also generalize it to more arbitrary domains, and there they could prove that there is an interval for which such a solution exists, but they couldn't give the exact bounds for this interval. So the proof is, again, by a classical method of variations. One looks at this functional and consider the minimizing sequences, and if P, this is a Sobolev, critical Sobolev exponent, so there is no hope, or at least in general, those minimizing sequences don't converge. And in order to prove the convergence, there is a very nice theorem, concentration compactness lemma, which goes back to Pierre-Louis Lyons and Thierry Aubin. And they proved that if the infimum which exists, if this infimum is smaller than the value, the infimum of the same expression, but with alpha equal 0. So this is the best Sobolev constant in the critical case. And this constant is independent of the domain. So if one can show that the infimum is smaller than this constant, then there exists a minimizing sequence which converges, and it's a minimizer, it converges to the solution of our problem. And they were able to show that this is really the case when lambda is in this interval or in this interval. And the proof is quite sophisticated, because one cannot just put any trial function in this quotient, because in general it will not give you that strict inequality if you just try anything. The common examples, it doesn't give you strict inequality, so one really needs to have a very sophisticated trial function, and they were able to do that, and so this could establish this theorem. And the non-existence proof follows from a Poiseuille type identity. I mean, you can you can generalize a Poiseuille type identity by taking different test functions, and if you do it in a clever way, then you just get this exact bounds. Maybe I should say one word about the case when lambda is equal to 0 and a general domain. So by Poiseuille, they don't exist solutions if lambda is equal 0 in a star-shaped domain. So the question remained open for a long time: what happens if the domain is not star-shaped? And one can see just one-dimensional calculus of variation. If you look in an annulus, you can prove existence for all p's, because in one dimension there are no restriction on p. And then there was the conjecture, maybe the existence of solutions depends on the topology. And Barry and Coron proved that by very heavy technique that in multiple connected domains there exists a solution for lambda equals 0 in 3 dimensions and p equals p star. And then the idea was probably there doesn't exist solutions for simply connected non-domain. But then the answer was able to show, he constructed a simply connected domain for which there is a solution. So somehow the topology doesn't seem to have such an influence on for the existence on the solvability of such a problem. So my idea was, probably also other people's idea was, to look at this problem on manifolds, because to ask what are the geometrical properties which are important for this problem, and the simplest manifolds to treat such a I should mention one more thing. We saw that for p larger than p star, there are no solutions if lambda is negative, but if Del Pino, Dolbo, and Musso could show that in this interval where there are solutions for the critical case, for p star, there are also solutions for p's which are close to p star. And in balls. And they construct solutions which have a bubble in the middle. And it turns, this bubble explodes or blows up when the exponent tends to when this p tends to the critical exponent, then the bubble blows up. So it's a very special type of solution they have been able to construct for the ball. So now I want to address the question, what happens in spaces of constant curvature? Because this is the other, at least to my, I think, one of the, it's the simplest way to tackle this problem. And there are two models, or maybe main models. The sphere. So we are looking at a sphere, an n-dimensional sphere, and we have to translate the problem to the n-dimensional sphere. And a useful way, at least for an analyst, to consider such problems is to project it to stereographically to the plane, or to the Euclidean space. So what is the stereographic projection? We look at, we have a point, say here, then we look at the line through the north pole, south pole, and the intersection, and map it, this point, to the intersection point in Rn. This mapping is conformal, preserves the angles, and therefore the line element has a simple form. It's just a factor times the Euclidean line element. So instead of working in this on this curved surface, I found it easier to work in Rn and with this metric. And one can compute the metric is 2 over 1 plus x squared. So the x is now a point in Rn. With this metric, the Laplace-Beltrami operator, the extension of the Laplacian to surfaces is simple. It's just this metric to the n minus n times the divergence in the Euclidean sense of r to the n minus 1 times the gradient. So the sphere has Gaussian curvature, curvature. All the principal curvatures are 1. And the second model with opposite sign, with a curvature -1, is the hyperbolic space. And a model for the hyperbolic, you can think of a hyperbolic space. You take a hyperboloid in Rn plus 1. So this is xn plus 1 to the squared minus x1 squared. So it's just a hyperbola in a n-dimensional space, and a Lorentz metric, which is given by this form. And if you look at this metric is not positive definite. So it's not a metric somehow in the classical sense. But if one restricts, the restriction to this hyperboloid is positive definite. And in this case too, we have a kind of stereographic projection, namely we can attribute to each point of Hn, we can find the line between -1 and map it on Rn by P star is just a map of is this projection of the Hn to Rn. And therefore, we can also work in, not in Rn. In this case, it's only the ball, because of, when you project infinity, you get 1. So we can work in the ball, in the unit ball in Rn, with the hyperbolic metric 2 over 1 minus r squared. And this is sometimes called the Poincaré model, the ball model of the hyperbolic space. And as before, it's a conformal mapping, so the Laplace-Beltrami operator takes a simple form. Now, I'm interested in the problem in geodesic balls in Sn or Rhn. So just think this is a Laplace-Beltrami operator. I just denote it by delta, but it means the Laplace-Beltrami operator. The problem is the same as before. The geodesic, the R is the length of the radius of the geodesic ball, and in the case of Sn on the sphere, it's only up. It's from 0 to pi, but in the hyperbolic space, the radius can become infinite. Now, as in Rn, there is an extension, a generalization of the moving plane technique, and one can show the moving plane method can be generalized to the hyperbolic space, and this was done by Kumaresan and Prajapat. And in this case, we have also the same situation as before, namely all positive solutions, if there exist, are radial. In the sphere, it's a little bit more complicated because the moving plane method, one has difficulties because there is this half along the equator. It's difficult to extend it over the equator. but it can be done if P is smaller than the critical exponent and if lambda is not too small. Then one can also show that all positive solutions of the problem in P, of this problem on the ball are radial. Now, the situation in Hn is very, I would say, similar to the situation in Rn, more or less. And this problem has been studied by a number of people. I have mentioned some. I hope I didn't forget some, but those are the one I know. So we have, again, for P less than the critical exponent and less than lambda less than the first eigenvalue of the Dirichlet, the linear problem, there exists a positive solution. If P is equal to the critical problem, we have again a similar phenomena, but the only thing is that the interval is shifted. In this case, we have, in the case of Rn, this was 0, and here what was a smaller constant. So there is a shift. And there exists a unique solution, so the techniques apply here too. And again, Poiseuille can be extended. We have no solution if P is bigger than this critical exponent, and if lambda is smaller than this critical lambda, and if lambda is bigger than the first eigenvalue. So the situation is quite similar. At least maybe I didn't try hard enough, but no, the uniqueness in this case, at least the method of Kwong and Lee doesn't apply immediately. Maybe one has to work a little bit more to prove uniqueness. I think there should be uniqueness. And also the existence of positive of solutions for near the critical exponent should be possible to establish in this case too. Now, the problems in Sn are a little bit, I have enough time, are a little bit more involved. And here we see new phenomena coming in. Yeah, first of all, the Poiseuille identity extends here too, but only for lambda which are not too small, too negative. So and the moving plane methods, as I said before, applies only in a certain range of P's and lambdas. So let me show you at least a picture. In the case of in the n equals 3, in the ball we have a in this case theta is the radius of the ball and lambda is this axis. So we have an interval where there exist solutions, there exists a positive solution, it's unique. And then we have regions where there are no solutions, and here there are no solutions. But there is a region where we don't know. So those regions can be, those solutions can be excluded by Poiseuille here too, but here Poiseuille doesn't work. And former PhD student, Simon Stingelin, he did some numerical calculations for small lambda, so for the lambda in this region I showed you before. And he found a lot of solutions. So we have solutions which have a concentrate near the equator, near the boundary. He found solutions which have a bump near the equator, and then there were solutions with two bumps, and then so he found all kinds of very strange solutions. And I showed this picture to Chung-Cheng Wei several years ago, and he said, oh, he can prove the existence of such solutions analytically. Yes. So the observation, this numerical observation, show there exist solutions, and if lambda becomes very small, we have solutions with more and more spikes. And those solutions exist also for values of p which are for any p larger than the critical exponent. So the critical exponent doesn't have any influence in this case. And Chung-Cheng Wei, he said his technique was to make a change of variable. He just rescaled the function, and then he looks at the very large negative lambdas, and with this transformation, one can reduce a problem to a problem with a singular perturbation. It's a singular perturbation model, a problem, and for this there are techniques which to prove the existence of solutions. I think it's not, there were many specialists in this audience here who know how to handle these techniques. I will just tell you the results. One can apply these techniques to small values of epsilons, that is to say to very small, small negative lambdas, and one can prove that for small lambdas there exist these three types of solutions which were on the pictures before. One gets solutions of those types, the one with a spike near the boundary, a spike with near the equator, a spike near the equator and the boundary, and those different types of solutions. One can prove the existence of those solutions analytically for small epsilon. And it is also possible to give the more detailed asymptotic behavior of those solutions. So what we get for very small, for solutions for, this method of singular perturbation gives solutions for very small lambda and arbitrary balls, which are big balls, which contain the hemisphere. And another method which gives information about for small lambdas, but for balls which are very large balls which are almost the whole sphere, can be done with a different method, namely the method of imperfect bifurcation. And I will just say a few words about it, to give you an idea. So the idea is for a negative lambda, one has a constant solution in the whole sphere. And one looks now for a solution which is a small perturbation of this solution here. And one linearizes it like the usual method of bifurcation method around the eigenvalues of this linearized problem, and then one can use the techniques of bifurcation techniques, namely to look for a solution which lies in the space of the eigenfunction, and the complement of the orthogonal complement of the eigenfunctions, and this solution here, but one has to truncate it a little bit because it's not this solution. This constant doesn't satisfy the Dirichlet conditions. So it's a little bit more involved than the usual bifurcation methods, but it can be shown that this method applies and gives solution for big balls, but small lambdas, not negative lambdas. And the lambdas near the eigenvalues of the linearized problem, which of the eigenvalues of the linear problem in the sphere, and they are known to have this. That's this expression. So close to these eigenvalues, there exist branches of solutions, and there I have a diagram. So those branches, in contrast to the classical ones, this is a solution, the constant solution. They don't emanate from the constant solutions, but they come very close. So I think my time is over. 1 minute, but one more minute. So this method, I think with this method, with both methods, we can also construct non-radial solutions for large balls and small lambdas. And the problem, we are now looking at the Neumann problem, and this seems, with Neumann boundary conditions, but this seems to be much harder. And I think I will stop here. Thank you for your attention.
Thank you very much. Now, please, questions. Please.
When you said at the end that for small lambda, did you mean large negative lambda?
No, lambda close to not the absolute value of lambda small. So yes.
So other questions, please.
Please, can you maybe, I'm sorry, but I have difficulties too.
If we consider the situation when we have one zero solution and one positive solution, and odd the evolution, I mean the derivative with respect to time, what you could say about stability of one or another solution?
I think they are not stable in the classical sense. The solutions are all unstable. The only stable solution is a zero in general in this type of equations.
No. There is example in population dynamic when p is equal to 2 and zero solution is unstable and positive stable.
So this I don't know. I know only the naive definition of stability, and in this naive sense, they are not stable.
Okay, so Willy?
I just want to remark to that it's very overlooked by people who do chemotaxis. it's close to this equation which you consider that most of them are unstable.
Yes.
Renard Deschamps has shown that, but
okay.
people do not remember that because this is not pattern anymore. Because you don't see them.
Yes. Thank you.
Other questions? No? Then thanks a lot again. Okay.
So you have the example of positive constant curvature and negative constant curvature. What could happen if you have a, say, compact manifold, but which curvature is maybe changing sign?
Yeah, that's not so easy.
No, I know, but
I think this would be the next step.
Concentration on one part.
Sure.
This
was the idea.
Curvature, for example, if suppose that you have a manifold with two parts, one has positive curvature, one other are negative.
I mean, part of the local the results you get by local considerations, like the construction of those trial functions and so on. This can be done and will probably depend on the proportion where it is positive, negative, and so on. But the global phenomenon, I really don't know what depends what curvature prevails, I imagine.
Because here in your result you use a radial solution.
Yes. This is
So, thank you. Other questions or comments? No, then thank you very much for your very interesting talk. So next talk will start 5 minutes to 1, yes, in 7 minutes.
Ты получила документы Кожевникова? Там никакие переводы и билеты. Все нормально? Спасибо. То есть этого достаточно, все нормально, да? Наташа, нет, я не кручу ни одну, я не критическую на заседании. Сейчас перерыв. Понятно. Наташа, еще знаешь, какого меня? А вот остальные, там же у нас, по-моему, 8 человек иностранцев. Все тебе дали гостиницам или нет? Понял. Ладно, спасибо. Ну хорошо. Подожди, нет, ну это не приглашенные докладчики, период это такие мелкие. Ну ладно, я вот так спрошу. Теперь, ты помнишь, что мы сегодня идем? Надо где-то 23 быть программным комитете. Ну я не знаю, как будет сказать, может он хочет один вести, а еще и пойдет. Это вы решите, мне неудобно лезть. Хорошо. Вот, и вечером идем, ты помнишь, да? Ладно. Ты Даша, да, надо Даша, дай трубку. Даша, дай трубку. Нет, туда я без русски 3 приду. Без русски 3 пойдем туда. Я еще на заседании, потом пойду покушаю. Алло, Даша. Даша, да, отлично. Я просил тебя дать трубку. Скажи мне, пожалуйста, а там всем по джериску какие надо тебе дали документы свои или нет? Вот вроде, да меня не интересует конкретные фамилии, просто я вам все ли сдали? Из 8 приглашенных докладчиков все сдали? А мне Наташа сказал, что они тебе сдают. Гостиница выдаст на соответственно докладчику, да? Все джериска. А вот мне Коломовская сказал, что один кто-то что-то не подтянул, или где-то еще. Ну, ты поговори с Коломовской, вы сравните, кто принес, кто нет, чтобы нас потом они уедут, как-то разбегутся и ничего не сделают. Ну ладно,
Okay. Yeah, that's it. So, quelques tours en bataille. Where's the phone?
So, moment. And,
That's...
so now, it's a big pleasure for me
back. Okay.
to introduce
Goes like
the talk of Professor Claude Bardot, who is very good friends of Russian mathematicians, and we met many times, not only in Moscow, but in some other places. And so, as I remember, we met last time with you in Baikal 2 years ago in Baikal Lake, and it was good, interesting conference. So please, so the talk is Vlasov-Dirac-Benny equations at the crossroad of spectral analysis and integrability. So it will be done by Professor Claude Bardot from University Paris 6, yes, and University of Nancy. So please.
Many thanks. That works? That works? Yeah, you can hear me. Okay, so many thanks. I don't want to add to things that were said yesterday, except that I'm very happy to be here, and I thank you for the invitation. And I will talk about the Vlasov equation. I move forward. There will be a special equation in my talk, which you will see, and that's where Vlasov is coming just after that. This equation will be the general thread of my talk. You will see why. Then, of course, I will talk. We'll use the modal analysis. We'll look at the nonlinear analysis of the equation and tell you why I like this problem, because it's at the cornerstone of a certain number of different ideas of mathematics and physics. Okay, so since this is a third talk on Vlasov, I will assume that after the talk of Professor Bat, Professor Sukachevsky yesterday, you are more or less familiar with the thing. I just wanted, since it's not known in the community of mathematicians, especially in France, I took this picture of academician Anatoly Vlasov from the web and the comment that you can read around it. Okay, so I move on. So this is the equation of my talk. It's, the characteristic will be that it's an advection equation which is coupled with a nonlinear coupling. The most important problem characteristics is that first, it will be in space a 1D equation, and second, in this equation, compared to the previous talk, the potential is a Dirac. And I will explain that in comparison with the other equation in the next slide. And that makes this as a problem at the crossroad of the semi-classical limit of the quantum mechanics, which was observed by Zakharov and then by others. And it meets an equation which was derived by Benet and picked after that by other people, Cooper, Schmidt, Manin, Teshukov. And in spite of being so simple, it has application in physics. Now, since it's a special one, I recall what is the standard general Vlasov equation. F is a function of time, space, and velocity, which is the density of particles. In this talk, the particle will be ions, but you can have interaction between different types of particles. And at variance with the talk of Professor Bat, there will be a minus sign in the energy. Then I have a potential V, which depends on the modulus of x minus y. Could be the Poisson standard potential. It's at the x minus 1. It could be the log, or more generally, in dimension greater than 3, minus d plus 2. But what is the essential part of my talk is that it will be a Dirac mass. Now, this just expresses the fact that the particles move by their velocity, and that their velocity is under the influence of a Coulomb force, which is derived from the mass by convolution with the potential. Now, a basic thing of this problem is that there is an energy, which is the sum of the kinetic energy plus the potential. And there is a difference with Professor Bat. Here there is a plus instead of a minus at the beginning of this morning. Main difference. Now, what will be useful for my talk is to take the Gateau differential of this energy with respect to F, very simply computed, and you observe later on that the Vlasov equation is really a genuine Hamiltonian system with a bracket, which is the standard Lie bracket with the variable x and v. That's a very, very forward computation, but I will use that like mad. Okay, now, physical motivation for this equation is that you start between ion and electron, and by an argument due to statistical mechanics, which has not been, to the best of my knowledge, put in mathematical form, you assume that the action on the potential of the electron is given by a Gaussian with coefficients which are small, which compare to the Debye length. So with that, you put this term equal to 0, and you replace this factor by 1 plus minus epsilon something, and you end up by the leading expansion of the log to the fact that you will have just the derivative of the density. And I quote several people, but they are from the French community. They have the advantage that I've explained this story in a language which is very user-friendly for mathematicians. Because if you find that in book of physics, it's not wrong, but it's less user-friendly for us. Okay, so the main difference is that if you have an operator at the level of mathematics, you have an operator of degree minus one, because you take a derivative, and in the standard class of Poisson, you have the inversion of the Laplacian and the gradient that gives you an operator of -1. So there is 2 degrees of difference, and that will have drastic consequence on the stability of the problem, especially that will be a nice way to look at the Cauchy problem, because things will be drastically different. Okay, now, if I want to do, beside mathematics, which is down there, I want to give some justification for my talk in a one-dimensional. First, you can reduce some spherical symmetric of the profile of the velocity to the 1D. It's useful for numerical method, and as I said, it is convenient to approach the mathematical analysis, in particular the modal analysis of the spectral problem, where you can follow some idea already old but quite useful due to Oliver Penrose. And that's the next step I want to do. So that's what I call the linearized problem. So in the whole literature of Vlasov equation, you have this book of Kral and Trivial Piece, where they linearize the equation and near a profile. And what will be a profile for me? Maybe I may put a picture. Since it's a distribution, just a picture, I will keep it, just a distribution. So here I have v, the variable v. Here I have the function f of v x t, x and t and fixed, and I look at this function as a profile function of v. There will be basically 2 different ideas. One is a simple bump. Just keep this somewhere. I won't use it. I want to have you just keep that here. That's the simple bump. And for instance, that the multi-bump profile. But this different bump have drastic difference as far as the stability is concerned. That was observed by Penrose in the classical equation, and it's much more evident in the present case. So what you do, you replace f by g of v plus a perturbation, put it in the equation, change delta f into f. That's enough. You just keep that. Then move the crank. Look at modes with frequency omega of k. Put it in the equation. Turn the crank. You arrive to a dispersion equation, which will be, let's say, in Fourier space, which is a very classical object in this type of literature. But then you have to find, if you have modes, to look at the omega, you have to solve the equation. And the issue is whether you will find, for arbitrary frequency, arbitrary modes of, say, of non-zero positive imaginary part, because that will give something that will behave very badly. Okay, so you do that, turn the crank, and you end up with this equation. And if you have a solution of that type, by Fourier synthesis, you can immediately construct solution of the equation. And since everything is you can do, in the linear case, you can use Fourier analysis that will tell you that if to take this initial data, if you have a solution, it has to be of this form. So far, so good. So then you make the analysis, and what's happened is that there is a big difference here with the Poisson, because in the case of the Poisson, excuse me, should go back. How can I go back? I'm going forward, excuse me for that. Is it back or? Yeah, first. Not an expert with this kind of thing. Let you relax. So, here I am. You see that at the level of the Poisson, there will be a 1 over k. So you will have, with the 1 over k square, you will just have solution for finite frequency. In terms of functional analysis, that would say that the linearized equation, you have a group of equations, the advection group, and the perturbation is a bounded operator. The spectrum remains in a band. Now, for my problem, in the present case, you will have a Fourier expansion, you will have 1 over k. So you obtain solution of the form, modes of the form omega star multiply k, and you solve this equation. So if you have a solution with a non-zero positive imaginary part, or même non-zero imaginary part negative, then if you have a rho hat of k here, you just look that you will have an exponential growing factor with time, and if the initial data is not analytic, immediately at whatever any Sobolev regularity, the thing blows up at time t positive. So you have initial data for which the problem is not well posed. Now, how you find the solution, what you to compare to this picture, you can do two things. First, you can prove that if you have just one bump, then the problem is well posed, the linearized problem is well posed. And the trick is a trick of Kruskal. I was very happy I saw that I found it by myself, but then people told me it's due to Kruskal. You look, if you have just one profile, you can write one bump, you can write G prime of V like minus H of V, V minus A. And you multiply, and you have this theorem which says that the energy minus H prime of V, you see E, H is increasing before the maximum, V minus A is negative, decreasing after, so H minus 1 of V is a positive weight. So it's a positive weight, you put it in the energy, this gives you an energy. Now, how you prove that? It's really simple. You replace f of v by h of v, f tilde, put it in the equation, and you find out that g prime of v, f tilde, which was in the equation, is just dt of v, f of v. And now you have a very standard equation in all this kinetic model, which is described the conservation of mass, which says that the derivative with respect to time of t and x is equal to the minus the variation of the current. It's called the Fick law in some sense. This is the gradient of the integral of v of fv. So you use this equation, move that above, and you get this nice relation. So that was the argument of Kruskal, say Kruskal-Bardos if I found it, and that says that if you have one bump, the linear problem is well posed, period. Now, to show you that the nonlinear may be not well posed, the standard argument for the nonlinear is a very nice argument of Penrose, which I adapt in this case. I want to solve, therefore, the same equation. There should be a g prime here. There is a typo. 1 over v, g prime of v minus v star. And I want to find if there are positive imaginary parts in this problem. To do that, I look at the map, omega star, lambda of V star, equal to this integral, which is a map from the half plane into the complex domain, and I want to see if 1 is in this map. Now, what's happened is that I can look at the boundary of this region, and the boundary will be the real axis, because it's the image of the real axis, and this is on this picture, you see. The lambda goes from the upper half plane to the complex domain. This line goes to a curve, so the image is inside, and the question is just whether 1 will be in this domain. And the curve moves clockwise, and you just have to use the fact that for the boundary, where I am, should go back. No, this is... No. How can I get back? How can I get back to that? No, I want to go back. No. Sorry for that. Now it's blocked. Doesn't work anymore. Sorry. Give me 1 minute more for that. Doesn't. What's happened? Okay. No, I would like to go back. Now, I'm going back this way.
Yes.
Yes.
This way you go back, this way you go forward.
Okay, that was the point. So here is the picture. I just go back once. If I look at what is this curve, you know, you just get the principal value of this integral plus you just get the IPG prime of V star plus the principal value. So that says that the point which cross the real axis are the point where you have an extreme, a maximum or a minimum of G prime, and this what explains this picture. It localizes the point where you cross, and it localizes the point where you cross, and it shows exactly how you can localize and have a criteria. Now you have very simple criteria. You take a simple 2 bump, you concentrate them, and you find that you are always an unstable mode. So the conclusion is, and of course I can try to do that for the extreme bump. So the extreme simple bump is the Dirac case, and this extreme double bump are 2 Dirac. For the Dirac, you find that there is no solution because there will be no imaginary number, solution of 1 over omega square equal 1. And if you take 2 bumps, you see that you may have solution whether these bumps are close enough, which make the instability, or far away enough near a stationary state. And this is measured after when you have renormalized the density, the distance, by a factor a squared being less or greater than 2. Okay, so you are with me. I move on, and then you look at solution of the form now where you have a bad term, and since you have an exponentially growing mode, there has been a machinery which has been developed essentially by Jan Gros, Walter Strauss, all these people, and their message is that when the linearized problem is unstable, then you can export this instability to the nonlinear. Here it's even more drastic. You can show that if the theorem which is above, which says that if you have an unstable mode, the problem is not well posed except in there are initial data for which the problem is not well posed except in the analytical initial data. Analytical initial data means in Fourier that you have an exponential decay which will tame the effect of this growing mode. So that's the theorem. And you have the counterpart of this theorem, which was a theorem proven by Jabin and Nouri, which was my entry port to this problem, which says that if you have analytic initial data, then for short time, everything is well posed, which is not surprising, but which maybe was not so easy to prove. So that's the situation from the linearized problem. Now I want to move to the nonlinear, and to move to the nonlinear following what has been done by Benet and Zakharov and others, I will explore examples which are related to fluid mechanics. Now, example related to fluid mechanics, I give you the first, the simplest one. I will look at solution of the Vlasov-Dirac-Benet equation, which will be of the form rho of t and x that multiply v, the delta of v minus u of t and x, which means, in fact, that the solution is just one wave of, and I will call it monokinetic. So if you play this game, you put that in the Vlasov equation, you end up that a necessary sufficient condition. By the way, now I have the name Dirac. I have told you why, because I have a Dirac as a potential. But you find out that the necessary and sufficient condition is just that dt of rho plus dx of rho u would be equal to 0, and dt of rho u plus dx of rho square plus rho square over 2 is equal to 0. Now, that turns out to be the classical, one of the classical fluid mechanic equation, which is a problem which is well posed for finite time. And the reason in my language, or in the present talk, why it is well posed is the following. If you look at the energy, which I wrote here, that was a term not so clear, but if you express that in terms of the variable rho, u, and rho square, that turns out to be a quantity which is strictly convex, locally near the initial data, and it plays a role of what Goodenough and Peter Lax calls an entropy. So you have an hyperbolic system with an entropy. You have an hyperbolic system with an entropy, which is well posed. Okay, I move one. Now, there was an idea, and I think this idea was due to Zakharov, to generalize this, instead of a delta, you put a delta against u of x and a, which depends on an extra parameter a, and you integrate with respect to a. Put that, once again, in the Vlasov equation, this ansatz, and you find a necessary and sufficient condition for the system to be a solution of the Vlasov, of the term above the f to be a solution of the Vlasov equation. Turns out to be a necessary and sufficient. Now, someone, I guess it's Zakharov, who observed that this is the same equation as the equation which was introduced by Benet for water wave, and that's the reason why I call it the Benet equation. Okay, now I compute the energy, and you see if I compute the energy for this one, believe me, you have always the kinetic, and then the potential energy, there is a square, but it's the square of the density. It's not the density square. So as a consequence, it may or may not be convex. And when it's not convex, you will not be able to use the Lax criteria for stability. And as an example, you go to the discrete case, you replace this f of x by a sum of delta L, so you have a finite or a discrete sum of equation, which turned out to be this equation. They have an energy entropy, and you look at this quantity, rho n u n square, sum of rho n square, and you wonder whether it will be a convex entropy or not, which will be related to the well-posedness of the system. And for instance, many people have done many computations for that, but I leave you as an exercise to look at the convexity of this entropy near the point 1 for the density 1, ρ1, ρ2 equal 1, and the velocity a minus a, and you find out, and it's not a wonder, that the entropy will be convex for a square greater than 2, and not convex for a square less than 1, than 2. It's completely in agreement with what I have told you about the linearized system. Okay? So the modal analysis is in agreement with what I said about the stability for the linearized system. Now I want to export to the nonlinear case the fact that I have a simple profile. So I will compare perturbation of a simple profile. And that's the next point for the nonlinear problem. I assume that I have a simple profile for initial data, which I will need, for technical reasons, I hope once we get rid of that, to be flat near 0. And I suppose that the maximum is at 0. So then I make the reordering of this profile, which is a classical trick. This will range from 0 to 1. I trace the line, horizontal line, with ordinate A. It cuts the profile at the point V minus and the point V plus, which turned out to be two functions, V minus of A and T, V plus of A and T, because this and X, because this profile moves with X and T. And I have this formula in terms of Heaviside function. This has nothing with the dynamic. This is just this picture transformed in the formula. Okay, now I found out that this distribution, this function, given by this formula, will be a solution of the Vlasov-Dirac-Benet if and only if the V plus or V minus for any A satisfied a kind of Burger equation, except that the rho is except that the V depend on A, and that the rho are coupled with all the different V plus and V minus by this integration. Now, you can also define rho plus of xTA, which will be V plus V minus. U plus of xTA will be V plus minus V minus. Since V minus is negative on my picture, this is always positive. You find U as the average of V plus V minus, put it in the equation, and you obtain again a variant of the Benet equation with this term 1 over rho square divided by 8, which will improve the thing quite a lot. Now, what's happened to this problem is that I look at the energy again, which has been now constrained to the fact of being near this profile. This energy, if I write it in terms of the V function, near V plus or V positive, V minus negative, and rho being positive, one found out that in V plus and V minus, this is obviously a convex function. And you write it in terms of rho, forget about the second term, this is enough to ensure the convexity for rho positive. So having constrained to the shape, to be a perturbation of that, from an energy which is anything, I have recovered a positive energy. Then I remember more or less first that if there won't be the interaction term, that will be a set of Burger equation. But then with the interaction term, I observe, I use the fact that I had a delta in the potential. So I can write the equation as dt of f plus dx of f of v. F is a pointwise operator in x and t, is independent. It's a pointwise operator on x and t, and you can define it as an unbounded operator on the tangent on the orthogonal space L2 of 0, 1. So that looks really like a conservation law. Now, what's happened for a conservation law? if you have a conservation law, I generalize that, you try to show that it is hyperbolic. Now there is a criteria which is necessary and which is sufficient and sometimes necessary is the existence of an convex entropy, which is exactly what I told you. Because if you have a convex entropy, you multiply by its gradient. And since it's a conserved quantity, it's a gradient of a flux. And since it's a gradient of a flux, you had a result that comes in elementary calculus class, but which can be generalized in the present case, which is that if you have something which is a flux of this form, then it's equivalent to say that the gradient of the entropy multiplied by the gradient of f is a symmetric matrix, which turned out to be this symmetric operator. So what a result which is known in finite dimension turns out to work perfectly well in this setting. That means that when you have a convex entropy, you can adapt all what is known and prove a theorem of local stability that will say that near a profile of that type, I will have a well-posed problem and not a badly posed problem. Now, to convince that this argument, if I precise this kind of thing, it's a complete theorem. Here it's more or less a meta-theorem. But if I make the computation the present case, and I don't want to give you all the detail, one find out that you have a local theorem which you will obtain exactly as in the theory of well-posedness of nonlinear hyperbolic equation following prescription of Lax, Godunov, and other people like that. So that's what you do. You need some regularity, and you arrive at a theorem, which is here. Assume that the initial data are well posed. The V plus is positive, the V minus is negative. You have some regularity on with respect to X, no regularity with respect to V, and you have a theorem of well-posedness, which in particular says that you don't need regularity in V. You could replace this profile by a profile that would be in the form of a staircase, which people in numerical analysis call the water bag, and prove the stability with respect to the profile. So that's a very nice theorem in this case. Very good. So now I want to go on the extending more or less the story, to make some remarks. So all what I have told you is that there is an energy. Whether it's a Dirac or another potential, since I am the opposite side of Professor Bath, I have something which is positive here. And this is, dividing the equation is the same thing as writing dt of f equal the Gatto derivative of E with respect to f and the Lie bracket with f. When f is equal to delta, you obtain that this form, where f for x and t given is an operator in L2 of the orthogonal space, and you get the Godunov condition, Godunov-Lax condition, and it's maybe for our community, it's interesting to observe that it's the same thing as the condition that you will get looking at the problem at this level for having quantity that will be conserved. So you have the same, the Lax-Godunov condition is the same condition as for any conservation of quantity for an Hamiltonian system. Okay, so that's the last part of my talk. I will don't use this idea, and keeping this in mind that I am dealing with Hamiltonian system, I want to compare the stability theorem, which I have described to you, with issue from the semi-classical limit. So what I've wrote here is that in the previous part of this talk, for the linearized and the nonlinear problem, the strong instability, which make the problem well posed or not well posed, depends on the structure of the initial data, which is related to the convexity of the energy entropy. The second observation is that with this introduction of the entropy, any Vlasov equation turns out to be an Hamiltonian system, which in some cases, when it's a Dirac, correspond to really the same issue as the lax entropy for the characterization. Now, to understand all these observations, I would like to go to the semi-classical limit, in some sense to show you that the nonlinear Schrödinger equation is the parent of the Vlasov equation, or the Vlasov equation, the children of the nonlinear Schrödinger equation, exactly like the Burger as a descendant of the KdV. Now, to do that in 5 minutes, or maybe it's 8, what I do is that I introduce an equation which is less known in our community, but is completely equivalent to the Schrödinger equation, linear or nonlinear, is the one which I called the Heisenberg-von Neumann equation. You take an operator, k of x, y, t, which is self-adjoint positive, with such that which are of trace 1, and with the trace with the Laplacian, note that W11, the trace of minus Laplacian k is less than plus infinity. This operator, you can diagonalize it because it's a trace class, and then you look at this evolution of this equation under the action of the flow defined by the Schrödinger equation with a potential. Whether it's a self-interacting potential, whether the potential is just phi square, whatever it may be, it's the same formalism. And you find out that in this way you can describe the Schrödinger equation, and the same thing either that k be a solution of this equation, which is the von Neumann-Heisenberg equation, or the fact that each of the lambda n of t will be constant, and this of this phi will be solution of the classical Schrödinger equation, which I've wrote here with an interaction. Okay, and you find out that this is this equation, and once again, it's a lax pair, and it's 1 over h bar, the Gato derivative of Fréchet of the energy, the commutator with kh. Okay, when you have done that, the standard thing to do is to take the Wigner transform of the operator. Taking the Wigner transform is defining this function Vh of t and x as the integral over 2pd that multiply the Fourier transform of kh of x plus h squared over 2y, x minus hy squared dy. When you have done that, you put it in the Schrödinger equation, you look at what is the limit of this quantity, and you find out formally that the limit will be the Vlasov equation, always, but formally, assuming that things converge. Maybe they converge, maybe they don't converge. But formally, it's always that. Formally, also the energy of the operator, which is a trace of minus Laplacian, the operator, will converge to this quantity, and also the von Neumann equation turns out to be exactly the Vlasov equation at the limit. So it's fantastic. Okay, now the point is that I have told you that the problem in some cases is well posed, in some cases it's not well posed. What I just want to say, and hopefully for the logic of the mathematics, that should be hopefully the same thing, that there is no contradiction between the stability theorem, which I have described before, and what people have done when they try to prove that you do have convergence of the solution of the Schrödinger of the Heisenberg equation modulo Wigner transform to the solution of the Vlasov equation, or this Vlasov equation. And in fact, that will be I don't make I just have 2 slides. I don't make new result. I just make a catalog of what exists to show you that it is not in contradiction, that it is the same thing. Now, first thing, assume that you have that the potential doesn't depend on K, that's linear. In this case, what I've described on the previous slide here is nothing else than what people call the veil calculus, and moreover, even it was very well known in the classical theory of pseudo-differential operator by a theorem which is due to Egorov in the 70s, that you do have convergence. But Egorov proved it with the Fourier integral operator for Mander, so it needs smoothness. What I'm interested in is not in smoothness. Now, if the potential is regular, there are many results due to Lyons, Paul, Gerard, Markovich, Moser-Poupeau for mixed state. Now, if you look at local in time for potential which are singular and Coulomb, and you can find, and there is a result which I could not guarantee, but it's more or less the extension of Jabin-Nouri, which says that if everything is analytic, okay, local in time, you have convergence. Everything is analytic means that the initial data should be analytic in X and nicely behaving with respect to V, like exponential minus beta V. Okay, now, if I look at the nonlinear Schrödinger equation, in this case, I look at the WKB limit, written like that. What I found out is that in this case, if I take an oscillating initial data, put it in the Wigner transform of this K, I obtain exactly a sum of wave, of monocynetic wave, exactly as it was done, one slide, exactly as it was done by introduced in the previous slide. So what is the situation for that? And that will be my last slide. So if n is equal to 1, don't to worry, you are in the case which corresponds to the Dirac in the beginning of my talk. You have convergence. This was proven by Grenier. And then also, and now if n is greater than 2, I guarantee for you that there will not be always convergence, because if you have just data in Sobolev space as regular as you want, because I have proved that the limit problem may be badly posed. The next point is that if D is equal to 1, and if you have just one mode, then there's a proof of convergence with inverse scattering for a short time, which has been done by Jean Livermore, Ketchup also by Zakharov, which recover the result here, but describe very well the convergence. That's the case where you go to a profile that would be a delta. Now, there are many things, derivation by Zakharov and all the people around him for problems which are more general. But they were really looking from an algebraic point of view at the structure of integrability. So in this case, they have results which are valid when the initial data are analytic. They have a lot of results comparing what are the conserved quantity and so on. But of course, if I play the game of putting that in Sobolev space, this result turns out to be wrong. But I think that it's interesting to compare what you need and what exists in different points of view. Thank you for your attention.
Thank you very much. Please, questions. Yeah, you have. Please, questions and comments.
Is there a connection between your results concerning wave in plasma and is there a connection between your results concerning waves in plasma and the Landau damping effect?
Okay. That was a very natural question. What you do when you look at the Landau damping, you deal with the Coulomb potential. Mm-hmm. So it's a situation which is different from mine. Then, for the first thing, so then the problem, you don't have instability for short time. because the omega of k, they are only at low frequency. But if they exist, that create instability for time going to infinity, which may appear in the behavior of the phenomena that will appear if you do the Landau damping. And once again, in this case, you have the linear analysis, which gives indication for the perturbation for the nonlinear. This is the key thing which has been, it's due to Landau, that's clear. As far as mathematical proof, you know that there is doing some commercial for France. There is Villani and Moore.
Yes, I know.
But their proof is all, it's a very big paper, it's 100 pages, but it's a
Landau and Moore.
Where, what?
Two authors about the Landau
But
effect,
basically it's
Villani and Moore.
At small perturbation of the linearized problem.
Thank you. And another question. Is it possible to generalize your results to the case of two-component plasma in multidimensional bounded domains?
With boundary?
Multidimensional bounded domains, not in the whole space R or RD, Rn, but in bounded domains.
I mean, the fact, this idea of Lax and of the fact that the energy, when it's convex, is a Lax Godunov entropy, is something which is very robust. And if you put boundary condition that will be compatible with the limit, let's say purely reflexive, for instance, or purely absorbing boundary condition for the particle, then it is not done, but I guess it should work the same. And OpenShift mentioned, but if you want to have compactness and easy Fourier analysis, you do that in a periodic box, and of course.
Thank you. Finally, I would like to mention only the following. Sorry for such remark, but Vlasov has never cooperated with Landau.
Yeah.
He was. Vlasov has never collaborated with Landau.
Actually, they are enemies.
I'll explain you later.
Yeah. Because I picked that from Wikipedia.
Okay, then.
We have to correct Wikipedia.
Okay.
I picked that yesterday
question?
from Wikipedia. Sorry for that. It's wrong. Okay, sorry for that. I told you I picked
maybe
that from Wikipedia. I was not
before
there.
maybe some moment. I would like to make some funny comments. And Vlasov, he was very unstandard person, and several stories about him is written in one paper of Maslov. For instance, he didn't believe that one can coincide 2 points by a straight line. Then he didn't believe to the existence theorem, for instance. Yes. So that is funny story. But of course, he was very great scientist. So please.
My question is the following. These equations that you, Vlasov-Dirac, are they natural come from some applications? What are their physical sense to some extent?
Okay, I told at the beginning there are two types of applications. First, that in some sense taking the derivative of the density is simpler, even if it's badly posed, than inverting a Laplacian. And this appears, so it gives a problem which is badly posed, but since you do numerical analysis, you truncate the high frequency, and in some regime, it may be, and the people people have been talking about in the plasma physics in Paris claim that they use it. The second thing is that the regime, which I described in one of the first slides, where the factor in front of the Laplacian, when you want to compute the potential, the real potential, in terms of the density of charge, is the factor is very small. It's called the quasi-neutral hypothesis, and in this case, in numerical approximation, you scratch it. So you put a 0. So then, that turns out that the potential is the balance between the ion that you want to construct and the charge created by the electron. Then there is an argument which looks to the standard argument of statistical physics, mathematical physics, which I don't understand, which says that in this case, the potential created by this, potential created by this charge, or plutôt this rather the charge in terms of the potential, will be given by a Gaussian. So you put the Gaussian, then you make a small variation. The Gaussian will introduce a log. You change what you want to compute the rho in the log of 1 plus rho. Log of 1 plus rho is equivalent to rho. That's my explanation for the general case.
And are there any stationary solutions of this equation?
What?
Stationary solution. And the first lecture of today's lecture, stationary solution.
Stationary solution, I didn't check for that. That should be an important. Oh, I asked Professor Barth a few minutes ago, what are the stationary solutions when you put a plus? And the answer more or less is that if you look at stationary solution defined on the whole space and you want them to be a finite energy, there is just zero. Because the things go away, and I don't know if, and we should give you a reference for that. But so stationary solution, the whole space is not, but in a periodic box there will be, and then that's an issue. That's.
So other questions? Yeah.
In case you have an entropy, can you say anything about T tending to infinity?
Okay, that's, if you look at the equation of isentropic fluid, which were the model which is variant, there have two equations. It turns out that if you mix the thing, you get as a consequence a third equation, which is the conservation of energy. For all this abstract machine, for all this machinery of hyperbolic non-linear equation, when you get a third equation by such a supplementary equation of conservation, which produces a quantity which is convex, it behaves like the standard Clausius entropy of fluid mechanics. And it has the property that with that you can prove that the problem is well posed, that you can symmetrize it, you can prove estimate. So that's the reason why it is just an energy with reference to the use which is done in this type of problem by Lax Godunov. I call it personally an entropy energy. Maybe I'm wrong, but it's an energy which in the problem plays the mathematical role of the entropy.
Thank you. Other questions, comments? So may I make some? I would like to attract attention to the people who study this Vlasov and Bainy equations to the old book of Maslov, which is called Complex Markovian Chain. Unfortunately, it was not translated into English, but nevertheless, it includes a lot of interesting formulas and ideas. It was published about 30 years ago. Then it's an interesting paper by Maslov and Fedoryuk about WKB and Landau damping. It was translated into English. It was published also about 30 years ago in mathematical сборник, математический сборник. Late 80, yeah. And then Maslov and his students Karasov and Chernych, they studied the stationary problem in one-dimensional and multidimensional case of Poisson-Vlasov equation, and this was published in some, I didn't remember now where, but there are several, maybe in theoretical mathematical physics, at interesting things that is based on Lagrangian manifold, and it's some difficult to construct the stationary problem. At least,
so you
yeah, I can give you, at least we can discuss later. And then also, I would like to attract attention to the recent paper of Maxim Pavlov about this Vlasov-Bainy equations and relationship with integrability. It was a recent paper, very recent. You see, he presented his talk at our seminars in last May, maybe. And so I think it should appear soon in Archive or maybe some other papers. It's integrability and it's a change, and so it's so thank you. Okay. So more questions, no comments, and so thank you very much again for your very interesting talk. Now the time is for lunch.
to come here to Moscow and also for the opportunity to give a talk here. Since bifurcation theory is not in the mainstream of the conference, I will first say a few words about bifurcation and equivariant bifurcation before I come to the main point which I would like to communicate. So my overview is bifurcation theory, some words about that, then a few words about results which could be motivated from applications, and then I come to equivariance and the EC conjecture. So equivariant bifurcation has many applications. I will show a few of them in fluid mechanical problems, in geomagnetism, in the development of the early universe, in liquid crystals, and it draws on many fields in pure mathematics like analysis, representation theory, harmonic analysis, Moline functions. Then it depends on dynamical systems, where you study heteroclinic cycles, stability, classification of systems, and so on. It uses algebra, group theory, you will see some of it, theory of modules and rings. Singularity theory is used, and topology and equivariant degree. Today I will only use a few of these items here. But it's a field with its in the center of mathematics in some sense. So dynamical systems could be discrete or continuous in time. They can live on various spaces and may depend on random perturbations, but I will discuss the simplest situation. My time is continuous. My system lives in Rn. I mean, the same ideas or the same results would apply to much more general context, but this is not what is important here, and there will be no random perturbations. And so in dynamic systems, we have notions of equivalence of systems, like topological equivalence, contact equivalence in the study of Golubitsky and others. And equivalence notions give stability. When equivalence is present in an open subset, you would call an element of this open subset stable, and this gives rise to a notion of bifurcations. So we call it stable, as I said, if there's a whole neighborhood which is equivalent within our chosen equivalence class, equivalence relation, and now we consider systems depending on a parameter, and we expect that the mapping lambda to f of lambda is sufficiently smooth. Then we have a bifurcation point if the system f lambda naught is not stable, and if in each neighborhood you have two different stable systems which are not equivalent. So this is a very general principle setting of bifurcation theory, and so we could also look at localized version, and locally it is sufficient for bifurcation if the number of equilibria changes or if the number of periodic orbit changes, and this is all we need for today, but this is also embedded in a broader theory. So let me just look briefly at some applications. In many applications, we have known trivial branches of equilibria. So if you look at the buckling of a column, you have the unbuckled state, and if you apply a load, then there's a state where this is a little bit shorter, but in principle, it does not change shape. So this will be the trivial solution in this context. Then if you have a Taylor-Couette flow, you have two rotating cylinders and a fluid in between, and there is a laminar flow in between these two cylinders, and we call this the trivial state of this medium. And in the spherical Binar problem, you have two concentric spheres. You have a constant temperature on the inside and the outside. You have a fluid in between, and you have the pure conduction mode, which is the trivial state. So you always have a trivial state, or in many cases you have a trivial state where you can start with. So you have a bifurcation parameter, which would be the load in the first example, the difference of rotation speeds in the second example, and the temperature difference in the third example. And in all three cases, you have a value of your parameter where the trivial branch becomes unstable. And this is the point where we are interested in. And Instability gives rise to new solutions. In some sense, we expect if the solution gets unstable, the system has to find a new stable point. And this is the motivating observation for the next couple of minutes. So one of the famous theorems is by Grendel-Rabinowitz around 1970. If you have a stability, if the change of stability comes from a single eigenvalue moving across the imaginary axis, then you have bifurcation in the sense that you have near the trivial branch a new branch which is non-trivial. So this x of s is non-zero, and this is a non-trivial branch. You could have more complicated objects arising which have the same Connelly index as your steady state before, but generically you see bifurcation to a new equilibrium at a single eigenvalue 0, and so this is what we are interested in. And genericity means that this is happening for an open and dense subset in your family of mappings which you are looking at, for example, in this space which I have written here. But this could be also more general. So let's come to equivariance. An equivariant dynamic system, you have a symmetry group which acts on Rn, and by this I mean you have in principle a homomorphism from the group to the group of On, and the elements of G act as orthogonal maps on Rn. And we have for our dynamic system the equivariance condition. It doesn't matter whether I act with G on X and then apply f of lambda, or whether I apply f of lambda and apply G afterwards. Consequences of this condition are equilibria come in group orbits. I mean, if this is 0, then of course the whole orbit G of X will be consist of zeros of this function. Fixed point spaces of subgroups are flow invariant. This is a very simple 3-line computation which almost everybody who talks about this presents, but I don't do that because you probably have seen this before. And you have a stratification in orbit types. And one important observation is if you have an equilibrium and if it's fixed under subgroup H and you have a non-trivial kernel for your f lambda at x naught, then this kernel is invariant under the group action, and there's an invariant complementary subspace to it. And by this observation, you reduce your equations to the kernel, and from now on, I'm only working on the kernel. So when I write Rn, I think that the Rn is the kernel of the mapping I look at. So we have a known branch. We have at lambda 0, 0 as an eigenvalue. The generic property is that the kernel is absolutely irreducible. What do I mean by that? If you look at a linear operator on this kernel, and if it commutes with all the elements of the group, then this is automatically a multiple of the identity. This is what we mean by absolute irreducibility. So all the commuting linear operators are the multiples of the identities. No other object commutes with the group elements. Eigenvalues cross imaginary axes. This we had seen in the Grendel-Rabinowitz theorem, and we assume that the system should find a new equilibrium state. So let's ask a question: when do we know that the system finds a new equilibrium state? So the first result in this direction goes back to van der Bouwhede, Sedinger, and Sigonia in various notations. They have proved that if this is smooth, if it's G equivariant in the second variable, if the kernel is an absolutely irreducible representation of G in the sense I have talked about, if the eigenvalue crosses the imaginary axis, this means that sigma of 0 is 0 and sigma prime is non-zero, so it crosses the axis. And if there's an isotropy subgroup which has a one-dimensional fixed point space, this is a crucial observation, all the other points are technical, then there exists a non-trivial branch of zeros of F with symmetry H. And what we do is we apply the Grendel-Rabinowitz theorem in fix of H. That's very simple. And as a corollary, we can observe that the same conclusion holds if we replace this condition, fixed age is 1, by fixed age is odd. The same thing holds true. And so if we conjecture that a loss of stability via an absolutely irreducible action leads to bifurcation of steady states, we could ask, how could one prove this? And this is what Issei conjecture is all about. Issei conjectured that if you have an absolutely irreducible group action, then you automatically have a fixed point, you have a subgroup whose fixed point space is odd dimensional. This is what Issei conjecture is saying. In each absolutely irreducible real representation, you have a subgroup which has an odd dimensional fixed point space. And by the argument we have just seen, this means immediately the bifurcation of steady states. So my question, whether this is automatically true, that loss of stability leads to equilibria, would be answered if the answer to the Issei conjecture would be yes. And so this is why I look at the Issei conjecture. So main question is Issei conjecture true? And the next part is joint work with Paul Matthews from the University of Nottingham. We have looked at some subgroups of R4, and what I want to show you is the failure of the Issei conjecture in dimension 4. So we have a 4-dimensional space. We present groups which act linear orthogonally on this space, and where this conjecture is not true. So we look at the following 3 series of groups. So M is an odd integer greater or equal to 3. And this is just indicating which of the families we look at. And this notation is taken from the book by Conway and Smith on quaternions and octonions, which is a very beautiful book, which I can advertise for. And if you don't know this notation, which I did not know before I looked at this book, then these are the elements, pairs of quaternions, which generates a group. The group SO4 can be represented by pairs of quaternions, which are multiplied from left and right with a given quaternion, and so you have a 4-dimensional action, and then this is the natural element 1 and I, 1 and J and E4 means one of the roots of I, and this is the mth root of -1. And so you have these 3 family of groups, and the groups have orders 48, 80, 112, 144, and so on, for k is 1 to 3. And what we have is, if you take 2 of these groups, and if M divides M prime, then the GKM is a subgroup of GKM prime. This is easy to prove in principle, but this implies that the closure of the union of all these groups for given k is again a group. In fact, it's a 1-dimensional Lie group, and so we have for each k one of these 1-dimensional Lie groups. The groups G1 and G2 are isomorphic. This is not a very important observation for what we are doing today. And we have the infinitesimal generator for the 3 groups is element Lk, which is given by the pair I1. What we have for these groups are that the natural action of these groups on R4 for JKM and JK are absolutely irreducible, so they satisfy the hypothesis of Issei conjecture. If M is greater or equal to 3, then you have at least 3 isotropy subgroups. Each isotropy subgroup has fixed point dimension 2, and so this is a family of counterexamples to the Issei conjecture. By accident, GKM and GK have precisely K non-trivial isotropic types, and you can write down how the normalizers of these isotropic types act on the fixed point spaces. This is one of the theorems from group actions, that you have actions of the normalizer on the fixed point spaces, but this is not what we need today. So There's a very nice computer program which is called GAP, which allows you to do group theoretic computations. And we find many more counterexamples to the EC conjecture. All these numbers listed here are orders of groups which lead to counterexamples, and these are the GAP names of these groups. GAP has a way of giving numbers to each isomorphism class of a group of given order, and so I have used this to design a group. And the red numbers indicate those groups which are covered by our theorem. So we had 48, 80, 112, and 144, and we had three of these 5 groups here in our theorem. And all the black numbers indicate groups which are not covered by our theorem. They have the same property, but we have no proof that they have this property. For the red ones, we have some proof. And also what you see is that the numbers which come up here seem to be a little bit odd distributed. You don't see a regular occurrence of these numbers, and so I will order these numbers in a different way. I write them in the form power of 2 times m, and then you see that you see all these numbers occur here, and you have and red means something different here. This I don't want to explain now what red means. There's also some information. But you see in the first column, which are groups of order 8 times an odd number, you have these 2 numbers up to here. And if you do continue the computation, you get these m's. And this is is a sequence of positive integers. It's contained in the encyclopedia, online encyclopedia of integer sequences, and it has a number there. I'm telling you this because you will see that I have 2 more of these sequences which are not listed there. I have studied the group, the first group. If you look at this order, then I have studied the first group here a bit more detailed, but I think for time reasons I will not go too much into that. Let's recall a theorem by a mathematician which lived in one of the Baltic countries many years ago, in the 19th century, Moline. He looked at the dimension of the space of homogeneous polynomials, which are invariant under the action of a group G acting on Rn. And he also looked at the dimension of the space of polynomial homogeneous maps mapping Rn into itself. And the question is, given G, how many of these polynomials do you find? And what he wrote down is this series, P of lambda, where these dks, which are the spaces of these, the dimension of these spaces of invariant polynomials, are multiplied with a dummy variable, and you look at dk times lambda to the k, and here you look at ek to the times lambda to the k, and then you find that these series are given by integrals over G of, here you take the determinant of the identity in Rn minus lambda, which is now a different lambda from the former one, this is the same dummy variable as here, not the bifurcation parameter, of course, and you integrate with respect to H measure or with respect to the counting measure on the group, and you do the same for R of lambda, where you write the same term and the trace here. Unfortunately, if you want to do the computations, this is a little bit difficult to do because these integrals are usually not so easy to compute. And so it would be nice to be able to determine the dimension of the space of invariant polynomials of order 3 or 5 directly from the group, and not by doing all these other computations. And there is a formula which goes back to Selinger, which is like follows. He takes the character of the group. The character of the group is a function which assigns to a group element the trace of the linear operator which you have assigned to it. And then you look at this complicated looking formula, and then you integrate this function he k over G and he k G times he of G over G, and you get directly the numbers dk and ek. And so with this, you can start to do the analysis of bifurcation analysis because you can write down algorithms to determine the equivariant mappings of a given degree. You can write down the equivariant Taylor expansion, and from this you can decide on bifurcation. And for the families which I have written down, we find bifurcation in the fixed point spaces which I have described. So in these counterexamples to the Isé conjecture, it's still true that you have bifurcation of steady states. And if you look at the Lie group, then you get a whole circle of such steady states. And if you look at the groups GKM, which I had, then they give isolated points on these circles, and you have a flow which is connect these equilibria on these circles, which are circles in the fixed point spaces of the group which was discussed. So this was the failure of the Isé conjecture in dimension 4. I just want to make a few comments on these Moline functions. The computation is usually very slow. The number in this Differential formula, this number of terms which comes up there is the same as the integer partitions which you get for the number k. But if you use programs to compute integer partitions, you can reasonably fast compute the low order dimensions there, and for chi 3 and chi 5, the formulas look like it's written down here. Let me go up in dimension. In dimension 8, I have a similar statement. We look at integers of order 64 plus multiples of 128, and for this we write down some complex numbers. With these complex numbers, dk1, dk2, and f, we write down some matrices here, and 2 by 2 matrices like here, and with these we write down these 4 by 4 matrices, and with and these now are this means this is a 0 in 4 dimension, 0 in 4 dimension, and S and T, which were 4-dimensional objects. S and T is written here, yes. So you have 8 by 8 matrices, and so we have defined a group which is generated by these elements rho 1, L to rho 2, and rho 3. And the theorem is that this group has these given orders. The orders are 192, are 320, and so on. You have a similar statement as before. If L prime divides 3L plus 1, then GL is contained in GL prime, and as a consequence, the closure of the union is again one-dimensional Lie group G in the group of orthogonal matrices in order 8. And natural actions are absolutely irreducible, and the only isotropy subgroups have fixed point spaces of dimension 2 and 4, and so in dimension 8, the Isé conjecture fails as well. Then we could ask, can it happen? This is a little bit different question. Can it happen that you only have 4-dimensional fixed point spaces? So you have dimension 8, have a 4-dimensional fixed point space, and a 0-dimensional fixed point space. Because this would mean that if you have a bifurcation, then in this 4-dimensional space you have a jump from 0-dimensional steady state to a 4-dimensional space. So you have a bifurcation. We have 4 eigenvalues cross with the same speed the imaginary axis. So this is considered to be an extremely degenerate situation if you have no additional structure. But if we have this situation here, then this happens generically. So very degenerate situations could come up generically. So I asked myself this question whether this can happen. And the answer is as follows. I have ordered again these numbers where you get these failures of the EC conjecture, which are again, most of these numbers are only computed by gap. You have if you have a y here, this means yes, so you have only 4-dimensional fixed point spaces. And if you have in the second component a y here, then this means that you have a single only isotropy subgroup, and this has a 4-dimensional fixed point space. So you have a very simple situation with a 4-dimensional bifurcation, so to speak. And so these are the numbers for the first for the odd numbers up to 85, and so you see that in the first column again you have always yes here, and you have in most cases the second also yes. So you get a sequence of odd numbers which are multiples of 60, whose multiples of 16 give you these numbers which are written here. And so what you see is that you have only 4-dimensional fixed point spaces happens if this number m, which here I have listed the prime decomposition of these numbers, have a factor of the form 1. If m itself has a factor of the form 1 mod 4, and the yes in the second entry comes up if you have a yes in the second column, and this means that one of the prime factors is of the form 1 mod 4, and both sequences are not contained in this online encyclopedia of integer sequences. So these are, in some sense, new sequences which have some meaning in bifurcation theory. Maybe I should add 2 more comments. One is that the groups which I have shown you in dimension 4 come up in a study which is independent from this one, where Pascal Chaussard and Olga Podwigina have studied a classification of heteroclinic cycles in R4, and so the same groups come up in their study. And the second question is goes back to the EC conjecture again. We have seen that we have counterexamples in dimension 2 and 8. And obviously the EC conjecture is true. This is a very easy exercise for third year or second year students, that in dimension 2 the EC conjecture is correct. It's very trivial. So the question is what happens in dimension 6. And in dimension 6 there's a theorem by Haibo Ruan, who is a postdoc at Hamburg, and she has shown that in dimension 6, every absolutely irreducible group action of a solvable group, finite solvable group, has at least one odd dimensional fixed point space. So this is of course an additional assumption that this is a solvable group, but from the proof I think it should be true that one can remove this hypothesis, but we haven't done it yet, so this is open. But the new conjecture could be that the EC conjecture is false in dimensions which are 0 mod 4, and it may be true, and it's at least true for n is 2, and it may be true in dimensions 2 mod 4. And with this conjecture, I would like to close my lecture. Thank you for your attention.
So, questions? Comments? Oh, please.
Oh, the references, sorry.
Settinger 5 number.
So my references are this is my paper. This is my paper with
American Mathematical
Paul Matthews.
Society.
It's on the archive, and the paper by Haibo Ruan has appeared in the Illinois Journal of Mathematics in the year 2011.
This is old, but 5 number, Settinger 5.
This is old, yes.
5 number. Second number. maybe 5 number new article.
This is from this is 2011, and my article here is 2010, and I have one which is on the archive, which I have not cited here, which is 2013.
В 2013 будет.
Symmetry break, мемуары.
So, next question. Comment. Well, let's thanks speaker again. And we have 4 minutes to the next lecture.
Это моя обязанность.
Я пытался однажды, ничего не получилось.
На эту тематику?
Нет, вообще, ну вот такой, как это, неожиданно перевод, ничего не вышло, что-то я не мог поймать.
Одна попытка ничего не доказывает. Не представительная выборка.
So the next speaker, Krainov, Anatoly Krainov, choosing the scheme technical solutions for the descent spacecraft delivering the automatic Planet rover.
Добрый день. Я представляю Московский авиационный институт.
I am
Работаю на НПО имени Лавочкина.
I am from Moscow State Aviation Institute and Lavachkin Corporation.
По имени Лавочкина занимается разработкой космической техники.
Our corporation designs spacecrafts.
И в ее портфеле имеется множество побед в этой области.
And we have a lot of achievements in this direction.
Например, это первые в мире посадки на поверхность Марса, Венеры, Луны.
For example, first successful landings on the surface of Mars, Venus and Moon are our achievements.
В моем докладе будут представлены прикладные задачи, которые возникают при выборе схем технических решений десантного аппарата с автоматическим планетоходом.
In my talk, I shall present technical solutions for. I shall present problems arising in technical solutions of automatic planet rovers.
Здесь представлен первый в мире планетоход. Это наш луноход-1, изготовитель НПО Лавочкина.
This is the first planet rover in the world. This is the legendary Lunokhod 1, manufactured by our company.
Актуальность использования планетоходов очевидна, поэтому на них подробно останавливаться не буду.
I shall not talk a lot about the motivation to use planet rovers because this motivation is absolutely evident.
На выбор схем технических решений большое влияние оказывают внешние условия на поверхности небесных тел.
To select a particular technical solution, we have to take into account conditions at the surface of various planets.
На основе анализа внешних условий разработана матрица проблем.
Analyzing the external conditions, we elaborate the problem matrix,
которая показывает, в каких подсистемах десантного аппарата с планетоходом какие системы, вернее, сейчас работают на каких этапах функционирования.
This matrix show which systems of the landing device with the rover act at each stage of the task.
И какие задачи требуют дополнительной проработки.
And which tasks should be investigated more carefully.
Например, это задачи управления с учетом запаздывания сигнала.
Examples. For example, control problem with the delayed signal.
Работа в условиях пыли, критических значениях температур.
The work under the conditions of dust and critical values of temperature.
Задача определения рельефа поверхности, точности перемещения.
The problem to define the shape of the surface and to define the exactness of the motion.
И так далее.
Etc.
На слайде представлена структурная схема десантного аппарата.
This slide presents the structural scheme of the landing device.
Он состоит из планетохода, системы ввода в действие и посадочного аппарата.
It consists of the rover itself, the system to start the work of rover and the landing device.
Каждая составная часть десантного аппарата имеет собственные служебные системы, специальные системы и полезную нагрузку.
Each component of the landing device has its own service systems. Какие еще системы, кроме служебных?
Специальные системы.
Special systems and useful load.
Нагрузка. При выборе схем технических решений планетоходов необходимо учитывать взаимосвязь этих систем и возможность их комплексирования.
Choosing the technical solution for the rover, one should take into account the connection between those systems and the possibility to unite them in a complex system.
Взаимосвязь показана красными стрелками.
The connection is shown by red arrows.
Красными стрелками.
Red arrows, yes.
Зелеными стрелками показана возможность комплексирования систем.
And green arrows show possibilities to unite various systems into a united complex.
Propustim слайд, потому что
Okay, the speaker skips several slides to be in the framework of his talk.
Здесь представлена классификация схем ввода в действие планетохода по способу посадки.
This slide presents the classification of the schemes to start the work of the rover according to the way of the landing.
Основным отличием при посадке является то, за счет чьих средств производится гашение энергии при ударе о поверхность.
The main feature to classify the way to land is how do you compensate the energy once you touch the ground, the surface.
За счет посадочного аппарата или планетохода.
You can use either the landing device or the rover itself to compensate the velocity once you are landing.
И в том и другом случае гашение энергии производится за счет корпуса, механических или надувных амортизирующих устройств.
In any case, you have only three possibilities to compensate that kinetic energy. Either the corpus of the device, or special mechanical devices, or special devices containing gas, inflated devices.
Приведу примеры взаимозависимости.
The speakers will present examples of interconnections.
Случаи 1 и 3, в которых при выборе таких решений необходимы малые габариты планетохода.
In the case of 1 and 3, to select such a solution, we need the size of the rover to be small.
Или случай 4, в котором планетоходу необходим ударопрочный корпус.
If we take the fourth possibility, then our rover should be resistant against collisions.
Примеры возможного комплексирования.
Now the speaker will provide examples of possible uniting of different systems into one complex system.
Например, в случаях 2 и 5 бортовой комплекс управления планетоходом может управлять также на этапах ввода в действие планетохода.
For example, the cases 2 and 5. In these cases, the control system for the rover also can be a system which starts its work after the landing.
Или случай 6, в котором надувные колеса планетохода гасят энергию при ударе о поверхность при посадке.
In the case 6, the inflated wheels of the rover are used to compensate the energy at the landing as well.
Здесь представлена классификация планетоходов по габаритам и массе.
In this slide, we classify rovers with respect to their sizes and masses.
То есть можно их поделить на легкие, средние, тяжелые.
So we can divide all our rovers into light ones, medium ones and heavy ones.
Классификация разработана на основе данных по отработанным и перспективным планетоходам.
This classification takes into account not only existing rovers, but rovers in progress as well.
Также планетоходы можно классифицировать по назначению.
Another way of the classification is the classification according to the purpose to use the rover.
Это транспортировка, исследование, ресурсообеспечение и так далее.
Transport rovers, research rovers, supplying rovers, etc.
Назначение планетохода определяет требования к техническим характеристикам планетохода.
The purpose to use the rover defines the requirements to its properties and characteristics.
Они, в свою очередь, обуславливают выбор схем технических решений планетохода.
Which cause the choice of the technical solution itself.
Ну, например, можно сравнить транспортный планетоход с исследовательским.
For example, compare a transport rover with a research rover.
Для примера все помнят лунный аппарат серии «Аполлон».
Probably everyone remembers the moon spacecraft of the Apollo series.
Хорошо. Транспортный пилотируемый планетоход должен обладать высокой грузоподъемностью.
A transport piloted rover should be able to carry a lot of weight.
Для этого ему нужна особо прочная конструкция.
Then its construction should be especially roof.
Требования влияют на выбор схем технических решений.
And this requirement defines the choice of the scheme of technical solution.
Или,
продолжайте, свет пока выключу, чтобы лучше было.
Или автоматический луноход в составе десантного аппарата должен иметь минимальные габаритные размеры.
On the other hand, an automatic rover, moon rover, being included into the construction of landing device should have minimal sizes.
И как решение данного требования – это складываемые элементы конструкции.
To satisfy this requirement, we use folding elements of the construction.
И так далее.
Etc.
На слайде представлены схемообразующие признаки планетохода и системы ввода в действие.
This slide presents the properties of the rover influencing to the choice of technical solution.
Для планетохода это характер полезной нагрузки.
For the rover, they are the substance of the useful load,
целевое назначение, габаритно-массовые параметры,
the aim of the rover, its sizes and mass,
тип движителя, тип связи, тип управления,
the type of the engine, the type of the connection and the type of the control.
Для системы ввода в действие это количество планетоходов, тип небесного тела.
For the system starting the work of the rover, they are the number of the rover, the type of the space object.
Компоновка в составе спускаемого аппарата и так далее.
The construction of the landing device, etc.
Красным показан пример выбора схемообразующих признаков для конкретного случая.
In red, you see an example of the choice of those properties for a particular case.
И в общем виде задача выбора схем технических решений представляется следующим образом.
The problem to choose the technical solution in its general form is presented on this slide.
Задано множество вариантов реализации десантного аппарата.
A set of the variants to realize, to design the landing device is defined.
Варианты реализации системы определены кортежем схем технических решений десантного аппарата.
Еще раз это предложение, пожалуйста.
А вот прям написано. Варианты реализации системы определены кортежем схем технических решений десантного аппарата.
The variants to realize the system are defined by a collection of scheme technical solutions of the landing device.
Каждое решение которого характеризуется вектором проектных показателей качества.
Each solution of the above collection is characterized by the following vector of the project quality parameters.
Это масса полезной нагрузки.
M small is the mass of the useful load.
Масса, габариты и надежность десантного аппарата.
M capital is the mass of the landing device itself. L is its sizes, and P is its reliability.
Необходимо произвести выбор схем технических решений десантного аппарата в обеспечении максимума массы полезной нагрузки.
So our problem is as follows. We have to make the choice of the technical solution to guarantee that the mass of the useful load is maximal.
При выполнении ограничений по массе, габаритам и надежности десантного аппарата.
Provided that the following constraints regarding the mass, sizes and reliability of the landing device are satisfied.
Показатели качества зависят от схем технических решений, от принятых схем технических решений.
The quality parameters depend on the chosen scheme technical solution.
Если позволяет время, я бы хотел еще рассказать о перспективных направлениях в области техники и технологии, которые определяют выбор перспективных схем технических решений. Это минут
10.
Да, 10. То есть рассказываю о перспективных направлениях в области техники и технологий, которые определяют новые схемы технических решений для планетоходов.
The speaker presents several particular scheme technical solutions which are in progress and which define the main tendencies in this direction.
Одним из перспективных направлений является создание целого роя простых и недорогих роботов.
For example, he presents a collection of simple and cheap robots, which behavior is similar to the behavior of, say, a fly family.
Такая разработка с учетом модульности и создания коллективного разума группы
taking into account that this group will have a collective ratio, a joint intellect, a joint artificial intellect,
позволит расширить круг задач.
We can extend the set of tasks faced by this device.
Повысить вероятность и снизить время их выполнения.
Not only to extend the set of those tasks, but also to increase the probability that the task will be fulfilled, and так, вероятность, наверное, повысить, а время понизить.
Да.
And to decrease the time to fulfill the task.
Создавать сложные структуры и распределять выполняемые функции.
There are also possibilities to create a complex structure and fulfill various execute various functions.
А также унифицировать составные части планетоходов.
Also, this allows us to unify the components of the rover.
Для примера покажу несколько видео таких разработок.
Okay, several videos will be shown just as examples.
We developed a nano-quadrotor capable of agile flight.
На примере квадрокоптеров рассматривается технология коллективного разума в группе.
You see quadrocopters with the joint group intellect.
То есть выполняются такие задачи, как совместное прохождение препятствий, слежение за рядом находящимся объектом.
They can execute the following task: joint overcoming of obstacles and following its neighbor.
Вот еще. Крутят восьмерку и не врезаются.
They simulate number 8 and do not collide each other.
Это видео как пример распределения выполняемых функций.
This video will show you an example how do they distribute the executed functions.
Существуют различные типы роботов, которые работают в команде и выполняют большую задачу, которую каждый по отдельности выполнить не смог бы.
So a team of robots execute a relatively big task which can't be executed by any particular robot from this team.
Достают книгу с полки.
For example, they extract a book from a bookshelf.
Пример модульности составных частей и унификации.
This is an example of the unification of components.
Каждый элемент может работать автономно.
Each element can work autonomously.
А могут все вместе.
On the other hand, they can work all together.
Принимать могут различные структуры, формы.
You see, the shape can be changed.
При этом изменяются их свойства.
And then the properties are changed as well.
Как, например, проходимость.
For example, they can change their shape to overcome obstacles.
Вот все вместе забираются на ступеньку.
This can't be done by just one component at all.
После этого трансформируется в другую структуру.
Once the task to overcome an obstacle is fulfilled, the system changes its shape accordingly.
Ладно, времени мало. Еще одно видео.
One more video.
4 минутки еще.
Робота научили складывать кирпичики и передвигаться по ним.
A robot is taught to create block structures and move along them.
Если такую технологию применить на Луне, то можно без участия человека построить лунную базу.
Using such a technology, for example, at the surface of the moon, we can create a moon base without any participants of humans.
Следующее направление – это использование искусственных мышц в движущихся частях планетохода.
The next direction is the usage of artificial muscles in moving parts of the moon rover, of the planet rover.
Это позволяет производить движение как единое целое, за счет чего снижается трение.
In this case, any motion is something like a unit action. So the friction is decreased, etc.
Повышается плавность, точность, сила передвижения.
The exactness, the force, and other characteristics of the motion are increased.
Вот, например, надувная рука.
For example, you see a pneumatic arm.
Как я говорил, для планетоходов важны габариты при транспортировке.
As I told, the size of a rover is important for transport rovers.
Как видно, надувная рука много места не занимает.
As you see, a pneumatic arm doesn't take a lot of space.
Ну и здесь показывается работоспособность ее.
And in the video you see what can it do.
Ну, не буду. Еще два направления – это альтернативные типы движителей.
Two more directions are alternative engine types.
Все они имеют свои достоинства и недостатки.
Each one has its own advantages and disadvantages.
Но их можно комбинировать.
But they can be combined.
И сочетать их достоинства.
To combine only advantages.
Например, гусенично-шаровый движитель.
For example, you see a combine of tank device with balls.
Или колесно-прыгающий.
This device has wheels, but also can jump.
Или
полминутки осталось.
Все, последнее направление.
The last direction.
Адаптивное управление.
Adaptive control.
Если по-простому, это адаптация к неопределенным условиям.
This means that we adopt in undefined conditions.
Наиболее распространенный пример — это робот Big Dog.
The most propagated example is a big dog robot,
который может передвигаться по различным типам поверхности и даже сопротивляться внешним возмущениям.
which can move along various types of surfaces and even resist external perturbations.
Спасибо за внимание.
Thank you for your attention.
Questions, comments? Let's thank the speaker again. So in 5 minutes we will continue.
Я хотела бы поменять просто, а куда этот поставить?
Давайте я как раз помогу тогда. Так, вам, наверное, презентер нужен будет. Нет, ну...
So let's continue. Next speaker, Professor Kostina, optimization methods for nonlinear model predictive control of non-stationary partial differential equations.
Thank you very much. And first of all, I would like to thank organizers, and I hope that they can hear me in the room number 410. So this is joint work or this presentation is based on joint work which was done together with the group of Professor Bock at the University of Heidelberg and also of my student Gregor Krivet. So the outline of the talk is why do we need nonlinear model predictive control for non-stationary partial differential equations. Then I will give you a short overview what is open loop control, closed loop control, and what is NMPC. Then I will briefly give you what numerical tasks we have to solve when we solve this problem and show you the progress in this area, namely multi-level real-time iterations, and will show you the challenges in this area. So why do we need non-stationary partial differential equations? So our motivation comes from applications. For example, the research is motivated by an industrial application of which is done at BASF company near Heidelberg, and namely an optimal control of a catalytic tube reactor for exothermal gas phase reactions. The mathematical model of this reactor is contain 2D non-stationary PDEs with suitable boundary initial conditions. The states in this model are temperature and EDAX concentrations, and there are some parameters which are catalytic and deactivation reactant rates, and the controls. And the controls in this problem are time-dependent throughput or dilution of catalyst by inert particles. So the aim is to use a mathematical model in order to actually to perform process optimization. And the aim of this optimization is, for example, one would like to improve the purity of reactor product, or at the same time reduce the amount of necessary catalyst or increase the productivity of the plant. And usually all this problem is subject to numerous inequality restrictions, for example, restrictions on temperature profile. So how are the nowadays industrial applications are controlled? So it is used by so-called real-time optimization, and usually the operations is performed in steady state. So, which means that as soon as some changes of specification of loads and of system parameters appear, one tries to re-optimize the steady state, and then go from one steady state to another steady state, so through transient phases, which are controlled by classical controllers, and often this is just rule-based control. So it's not mathematically optimized control, but like a recipe, rule-based control. And so, as I said, the usual application is in steady states. However, nowadays, non-steady operations becomes more important because it has enormous potential for improvements in transient phases, in startup and shutdown phases, and also in periodic operation. So nowadays, non-steady operation is taken more and more attention in industry. So the next question is, why do we use nonlinear model predictive control? And the thing is that there are uncertainties in the model. Also, we have seen this in the previous talk. There are uncertainties in model parameters, which can be varying and also can be unknown. Also, there are model inaccuracy. Namely, if we make some model, we make necessary simplifications. Also, there are some unmodeled effect. For example, in example of the rover, so there is you don't know the surface where the rover actually lands, and also there is an accurate realization of optimal controls. And as a result is that if we have this modeling errors, then real process will never follow the offline computed optimal solution. And hence we have to make some feedback controls, some controls that take these perturbations into account. So this is done with the help of closed loop control, in special case nonlinear model predictive control. So what are the optimal control problems that we solved? So we have some some model, which is, as I said before, is a PD model with appropriate boundary conditions. So we have initial conditions on the states and on the parameters. We have some control constraints, and we have the control, and here we consider the control that are just that only dependent on the time. So they do not depend on state. It's not distributed control, but there are some controls which are applied pointwise. So, and then we have some cost functional. So we solve this problem in some way, and then we get the solution, which is a time-dependent optimal open loop control. So we have the control that depends only on time. But of course, we have some disturbances or uncertainties, and in this case, we would like to have the control that depends on the state and on the parameters. So this means that we would like to have so-called closed loop control. So one can just how to compute this control. So one of the one of the possible solution to this problem is then as soon as we have some new state values and some new parameters values at real time, then we solve disturbed open loop control problem. So we solve the same problem, with the only difference to the previous problem. So we just change here initial conditions on the states and on the parameters. And then we get some time so that we get some function of time. And then we just take the first instant of this control and apply it into the system. And then in the next instant, we solve again this problem again for the new values of the states and parameters. And just doing this, we get a so-called optimal closed loop control. But of course, the problem is that usually we have to get the solution of this problem fast enough. So we cannot solve this problem from scratch for each new initial value for the state and the parameters. So what is nonlinear model predictive control? This is a special case of optimal closed loop control, and the idea is that the final times move together with initial times using some prediction horizon, and this prediction horizon actually, this is an approximation of infinite time. And so we again minimize the objective function over this time horizon. We have initial conditions on the states and on the parameters. We have PDE model, control constraints, and plus we have special additional inequality constraints actually on this term here. So, and again, we solve this problem. We get some control, and we apply the first instant of this control into the system, and if we do this at the next time point, we get so-called NMPC. So the control principle of this is we just look ahead. So we have this prediction horizon, and which is moving, and we optimize along this horizon. So one can see this principle on a very nice example, which is due to my colleagues from Heidelberg. So here we can see the one-legged hopping robot, which is actually, so this movement is so-called open loop stable against small perturbations. So this means that if we have small anyway, so the previous movement was, so the robot was hopping, and it is actually open loop stable against small perturbations. But if we have large perturbations, like for example the steps, then the open loop optimal control will not be able to take these perturbations into account. But if we make a prediction over this horizon, so if we will see this obstacle before we will predict the obstacle, we will take it into account, we can actually move through the steps. And this is this example showed just this nice principle of model predictive control. Okay. So next. Okay. So now the numerical tasks that we have to solve in this problem, and here we have actually two problems to solve. One is the problem in the past, and another problem is for the future. So for the past, we have some past controls, so we have some process and we get some data about this process, and using this data from the past, we can actually estimate a current state and parameters. So this is done through so-called moving horizon estimation problem. And then as soon as we get these new estimates for the states and parameters, we must optimize optimal control, so we have to solve optimal control problem, which is done with this nonlinear model predictive control. And as I said before, we just apply first control instant to real process, and as a result, we get a feedback law or closed loop control. So what we do for the NMPC, so basic numerical approach, we use finite element in space, we use discontinuous Galerkin in time. For control discretization, also we use special technique called multiple shooting time domain decomposition, and we use direct optimization approach. So after using all these numerical procedures, we get up a finite dimensional optimization problem with a large number of optimization variables, which includes discretized state and control variables. We have in this problem equality constraints that includes discretization model, and we also usually have a lot of inequality constraints. And so this problem is solved with specially developed Gauss-Newton method, so dependent on the cost functional, which is appearing here. So it is Gauss-Newton method, or other variant of reduced SQP method. So as a result, at each iteration, we solve some quadratic sub-problems with equality and inequality constraints. And since we get, there is one numerical trick here. So we have here the discretized variables include discretization of control and on the states. So there are, of course, special structures in this discretization schema, and so we use reduction. We may perform reduction by multiple shooting and initial conditions, and as a result, we get so-called condensed constraint quadratic problem only in variables delta W, which are here just the control variables. So using a special technique, we can reduce all state variables, all discretized states and parameters, as well as these initial conditions here, and we get the problem, which is probably also can be large if we have a lot of controls, but the sizes of these problems is much smaller than the sizes of this huge discretized problem. And also there is a special trick like embedding of initial constraints here, which allows actually to pre-solve this problem before knowing the actual states and actual parameter values. So this is why we need this, because we would like to make solution real-time feasible. And one of the approaches is multi-level real-time iteration. So first of all, what is real-time iteration? This is already quite an advanced technique, and the idea is to dovetail real process and optimization. So the idea is that there are two phases in iterations, namely is a feedback phase which means we compute feedback control from the condensed QP and we use it immediately in real process for some period of time. And during this period of time, we prepare the next phase, the next feedback phase. So we compute function values, gradients, Jacobians, Hessians, QP decomposition, and so we need for computing this, for example, we need to solve several PDEs. So in this preparation phase. So what are these multi-level real-time iteration is, and the general principle is that we do not iterate until convergence. So we do not solve the optimization problem until convergence. Just while preparing the next iteration, we reuse already computed information and we use this information immediately to refine the constraint closed loop control. And this technique showed to be very efficient for the systems described by ordinary differential equations or by differential algebraic equations. So the variance of real-time iterations, depends on which information we have. We can already try to compute new feedback laws. For example, as soon as we get new state and parameter estimate, we can just plug into this quadratic problem, which is solved during the SQP method, so if we plug in the states and the parameters, we get this delta W, so we get immediately the control response, and we can immediately apply this control into the process. And if we do this, we can show that we get so-called linearized inequality constraint feedback control, and this basically equivalent to solve this QP, which means we just have to make matrix vector product, which is very quick. And for example, in numerical computations for catalytic tube reactor, this level A cost about 0.056 of the second. So the next level, as soon as we solve our PDE problem, so we get a new constraint right-hand side, we can plug in this right-hand side in the QP, and also we can solve this with new right-hand side. And if we iterate to convergence, so if we solve the SQP to the convergence, then we get linear convergence to feasible suboptimal feedback control. And the cost per iterations here is one forward solve, so one PDE solve, and also we have to perform some condensing recursions in this problem. So, now I can see that this is more expensive already because, for example, for catalytic tube reactor, this procedure costs 2 minutes approximately. Okay, and then there is next level, level C. This means that as soon as we get new Lagrange function gradients, which is more expensive, of course, here, we can plug in, solve this quadratic problem, and we get already. So if we also iterate to convergence, we would get linear convergence to feasible optimal feedback control. The cost here, one forward solve plus one adjoint solve of discretization scheme, so which is approximately 4 forward solves. So all in all, 5 forward solves are necessary in order to perform the scheme. So the example I show you how it works for ordinary differential equations. So here we can see an optimal closed loop control of a chain. And one can see here, so if we excite the chain, then we just get some uncontrolled motion. And here, this is a system of 57 nonlinear ODE. And without damping, this is just a chaotic system. So one can see how long it takes to stabilize this chain. And then if we make the NMPC, then one can see here we get very quick stabilized the chain. So, and also I would like to say here that just one full SQP optimization will take 15 seconds. So in 15 seconds, of course, if we apply after 15 seconds the optimal control, then already we have different system to solve. And probably since my time is over, I stop here, and everybody who is interested, I can tell you the challenges, because it is actually, the problem is that it is still not real-time feasible for PDEs, and this is the challenge. So thank you for the attention.
So let's thank the speaker. Questions?
I ask you your challenges towards PDE, because usually in numerical situation you need enough regularity. No? For instance, I could imagine if you have transport equations, we get all the problems that smoothness is not good enough. Or what do you think what would be needed in order to have the information what you need for instance, for these problems with catalysis?
So for these problems, actually, we need to combine moving horizon estimator and optimization. So now there are two distinct problems to solve, and so we have somehow to see how the data goes immediately to the control. So I mean, this is the numerical challenge, of course, what I'm talking about here.
But is that also, I mean, for instance, I remember when we were looking at problems of catalytic reactions in such structures, if you had first order, then usually you have you have transport systems where you do not know enough regularity to go, for instance, to the adjoint problems. Are you jumping in such problems too? Which are analytic problems which you would like to be solved, not by your students, they have to do the other problems, but have you had such problems coming up in this?
So in this particular example, there was not such kind of problem. So well, how to say, actually the PDE model was very much simplified in the sense of that this type of problems do not appear in this case. And we were now interested more in the numerical procedure, how to perform this numerically very quickly.
So, more questions, comments? Thanks, speaker again.
Before the break, we have an announcement from the organizers.
Dear colleagues, the organizing committee reported me that some participants didn't register yet. Please come to organization committee. This is room number 410, and make all arrangements. Thank you.
So, our session is over, break right now.
We will start again at 5:25.
So this is the outline of my talk. So first I'd like to introduce the biological background, and then in the mathematical model part, we should determine the process to be modeled and derive the equations in the model. And I also like to introduce the numerical methods and show some recent numerical results. And the last part is the conclusion and outlook. So first I'd like to introduce the biological background of this problem. So the atherosclerotic plaque evolution is the whole process of the formation and destabilization of plaques. This is one of the main causes for the blockage of main artery. So here, this is the picture of real artery where plaques are formed. We can see that the blockage happened at this point. So this can lead to ischemic brain infarct, heart attack, and some other cardiovascular diseases. And to understand how this can happen, we need to identify some key steps leading from a normal artery wall to an atherosclerotic plaque. So this is the picture to show the whole process of the evolution of plaque. In the first picture, we can see that the blood vessel is healthy and there is no plaque from the inside. And in the second picture, we can see that the endothelial layers are activated and they release some receptors to attract these molecules with green colors, which is called monocytes, a kind of white blood cells. So the monocytes start to penetrate into the vessel wall. And in the third picture, when the monocytes penetrate into the vessel wall, they take up lipid proteins and finally differentiate into foam cells, which are full of lipid. And the accumulation of foam cells will finally lead to the formation of a plaque inside the vessel wall. So from the first picture of this slide, we can see more clearly about the structure of the plaque. It consists of two main parts. One of the parts is called the lipid core, which is formed by the foam cells. It's very soft and occupies a large volume of the plaque. And the other part is called the fibrous cap. It's formed by smooth muscle cells and separate the lipid core from the lumen of the blood vessel. This is the very thin layer. So this structure can not just narrow the vessel lumen and also make the plaque be vulnerable. So if the stress applied on the fibrous cap reaches a critical value, the rupture of the fibrous cap will happen. And then we can see that in the second picture of this slide, the rupture happened at this point, and the material inside the lipid core will be released into the lumen. And then a thrombus will be formed upon the plaque to finally block the vessel. So after understanding the biological background of this problem, we need to determine the main contributors to the development of plaque growth. And they can be categorized as either biochemical or biomechanical ones. So the main biochemical process should be the penetration of monocytes and accumulation of foam cells in the vessel wall, which can lead to the growth of plaque. And the main biomechanical forces should be the stresses applied on the vessel wall and also from the blood flow, which may lead to the rupture of plaque. So the goal of our project is to derive a model to describe the evolution of plaques and also compute the stress distribution in the vessel wall, which might lead to the destabilization and rupture of the plaque. So the main processes we would like to model are the first part, it's the biochemical process about the adhesion and penetration of monocytes in the vessel wall. And the second part is also the biochemical process, the accumulation of foam cells in the vessel wall leading to the plaque growth. And the other two parts are the biomechanical one, which is the influence of the foam cells to the mechanical property of the vessel wall and also the interaction between the blood flow and the vessel wall. So this is the computational domain we are considering. It's divided into two parts. The upper part is the fluid part, which is occupied by the blood flow, and the lower part is the solid part, which is occupied by the vessel wall. And the interface can move due to the fluid structure interaction and also the growth of plaque. And in the center part of the interface, this part is permeable for the monocytes, so that the monocytes can move from the fluid part into the solid part through this center part and finally lead to the formation and growth of plaque. So this is the list of the main variables we are considering. So we consider pressure, velocity, and concentration of monocytes in the whole domain. And especially in the solid domain, we also consider the density, displacement, concentration of foam cells, and another special variable which is called the metric of growth. I will introduce the definition of this variable later. So all the variables are distinguished by the index F and S in different domains, and all the equations are derived in Eulerian coordinates at first. So first, let's take a look at the equations in the fluid domain. We use Navier-Stokes equation to describe the fluid dynamics of the blood flow, and the convection diffusion equation to describe the motion of monocytes. In the solid part, the equations are more complicated. We use elastic structure equations to describe the structural mechanics of the vessel wall. So the first equation is the mass balance equation compared to the general one. On the right-hand side, there is a growth function which implies the growth of mass of the blood vessel. And the second equation is called the momentum balance equation, and sigma S is the stress tensor which will be derived later. And the last equation shows the fact that in the solid part, the velocity is equal to the material derivative of displacement. In the solid part, we also consider the motion of monocytes and foam cells. So we also use the convection diffusion equation to describe their motions. But on the right-hand side, there is a function which is called reaction function, implying the fact that when the monocytes migrate into the vessel wall, it will differentiate into foam cells by some chemical reactions. And this is the transmission condition on the interface. We have the balance of force and continuity of velocity, and the flux of the concentration of monocytes should also be continuous and also be dependent on the difference of the concentration on the interface. Now let's go back to the momentum balance equation to derive the stress tensor sigma S. Usually, sigma S is determined by the deformation gradient, but here in our case, since we consider the growth of plaque, so there should be a problem. Here is the very simple example to show what the problem is. If we apply the force on an elastic rod, it will be deformed, and the force applied on the rod should be proportional to the displacement. But if the rod is also growing when we apply the force on it, there will be some new elements from the inside the rod, and the force will not be proportional to the displacement anymore. So this shows the fact that the growth may falsify the usual way of quantifying the deformation. So to solve this problem, we need to decompose the deformation gradient into two parts. One part is the deformation gradient induced only by growth, and the other part is the deformation gradient induced only by mechanics. So in this picture, omega 0 is the reference configuration, and it's deformed to deformed configuration by deformation gradient F. Now we decompose it into two different tensors, G, S, and F, E, S. So then the reference configuration will be deformed first to another configuration, and then to the deformed configuration. This new configuration is called the natural configuration, and the tensor G is the deformation gradient only induced only by growth, and it's also called the growth matrix. If the other tensor FES is the deformation gradient only induced by mechanics, and the stress tensor should be dependent on this deformation gradient. If we assume that the growth of the tissue is asymptotic, then the growth matrix can also be equal to a scalar function times the unit matrix. And this scalar function is called the metric of growth, and it should satisfy this equation according to some literatures from Ambrosi and Monica, and also the PhD thesis from my former colleague, Doktorsky. And if we can solve the metric of growth from this equation, and then we can solve the deformation gradient only induced by mechanics by dividing the deformation gradient with the metric of growth. And then the stress tensor can be determined by this new deformation gradient according to the constitutive equations. Here we consider different kind of material, the incompressible new hooking material and Mooney rippling material. And in addition, we also consider the influence of foam cells to the mechanical properties of the tissue. So that means all the coefficients in the constitutive equations should be dependent on the concentration of foam cells. So after deriving the mathematical model, we can do some numerical simulations. But here, there is a main difficulty of numerics, which is that all the equations are formulated in the moving domain. So we need different meshes at different time steps. So to treat this problem, we need to formulate the whole system in one common coordinates, which is called ALE coordinates, arbitrary Lagrangian Euler coordinates. And in these coordinates, all the equations are rewritten in the fixed domain. And to construct the ALE mapping, we need to obtain the artificial variable of the displacement in the fluid part, which is defined by harmonic extension. So this is the variational formulation of our system in the ALE coordinates. This is just the part of the fluid structure interaction problem. The blue terms are the terms from the fluid domain, and red terms are the terms from the solid domain. And here, sigma f is defined, the stress tensor defined in this way such that Navier-Stokes equation is satisfied. And this function is just the function on the outflow boundary, so that the do-nothing boundary condition of Navier-Stokes equation should be satisfied on the outflow boundary. And for the rest part of the system, their variational formulations can also be written. So this is the equation for the metric of growth, and these are the equations for the motion of monocytes and foam cells. So after deriving the variational formulation, the numerical simulations can be performed. So we use the software Gascoigne, which is developed by the numerical methods group in the University of Heidelberg. And The time discretization is achieved with the implicit backward ordering scheme, and the spatial discretization is based on the Galerkin finite element methods. The system is very nonlinear, so we also need to linearize it and solve it by Newton method. So this is the initial computational domain of our numerical simulations. So the upper dashed line is the interface between the fluid and the solid part. And the center part of this line is with the color of red, and this denotes the interface which is permeable for the monocytes. And there is a very thin layer between two dashed lines in the solid domain. This layer represents the endothelial layer. From medical point of view, in this layer there is no chemical reaction of monocytes, so monocytes will just move through this layer into the deeper part of the solid domain. And in this numerical test, we consider incompressible neo-Hookean material as the material of the vessel wall. So this is the numerical results. The first picture is about the description of the velocity in x direction. We can see that at the initial time, this white line, the interface is flat. And after time about around 521 days, we can see that the interface has moved due to the formation and growth of plaque. And from this video, we can see more clearly how this interface is moved due to, as the time passed, the plaques start to be formed and grow. And there will be two humps around the permeable part of the interface. So this is the distribution of the displacement in y direction of the solid domain. And we can also see that the deformation reaches the maximum value around the permeable interface. This is also a video to show how the deformation is performing. And here there is a distribution of concentration of monocytes in the fluid domain. So at the initial time, we assume that the value of the concentration is constant. And when the plaque is formed, we can see that the concentration of monocytes will decrease a lot after it moves across the permeable interface. That's because some of the monocytes will just move through the interface into the solid domain. And this is the distribution of the concentration of foam cells in the solid domain. You can also see that at the initial time, the concentration is equal to 0. And so when the plaque is formed, we can see that the concentration is at very high at the place under a large deformation. So we can also see it more clearly from the video. As the plaque is formed, the concentration of foam cells will increase. So the last picture is the distribution of principal stress. So the maximum value of the stress reaches the stress value reaches the maximum value around the permeable interface where the deformation is the largest. And this is also the place where the critical value may be reached. So the rupture of plaque may also happen around this hump. This is also a video of to show the evolution of the value of the stress. I'm sorry, I think my time is over, and finally I will show the conclusion. We treat a mathematical model consists of the fully structured interaction problem and reactive transport problem, and the numerical results obtained so far show that the penetration of monocytes and accumulation of foam cells can lead to the formation and growth of plaques. And this evolution can also induce the increase of stresses on the vessel wall, which is an indicator of plaque rupture. And we also have some outlook of our work, considering more chemical reaction or some other realistic description, and also perform the numerical simulation to get better results. So that's the end of my talk, and thank you for your attention.
Thank you very much. I think we have time for one or two short questions. Are there any questions? Yes, please.
I have the impression from what you showed is that these plaques are very slowly growing.
Mm-hmm,
but
definitely.
But in reality, I know, for example, from atherosclerosis that the plaques are growing within a few days, and that there seem to be very nonlinear terms somewhere hidden that are not reflected by your model. Can you comment on this?
This is very interesting because we also have some collaborators from the Faculty of Medicine, but from their point of view, they think the formation and growth of plaque is a very long time period. It may take several years, maybe more than 10 years, but some of the patients maybe will be faster, but it still takes several years. So in our model, we consider the time scale with the time unit of at least days or even years. So I don't know whether the definition of plaque, whether the plaque has some other definition.
Atherosclerosis is not the same thing, but also their statements is for that too. They may have had a long time history before this breakout. And they claim that this what is going on. It's just starting. What he does is just the first period.
The question is, what happens when
After,
fast growth happens?
This is not in the model yet, and also one has to. He pointed it out. We neglected the heartbeat. And this even small time, compare that, it's really a challenge to everything, to mathematics, to computation, to measurements, everything.
I think we have no time for further questions, so let's move on. And thanks, speaker, again first. Where's the next speaker?
Between two talks?
Yes, but we are already.
Ah, I see.
I shall translate. Но мои вам вряд ли помогут. О.
So you're ready? So our next speaker is Alexei Invanyukin, and he will speak about minimum thrust problem as beginning of interplanetary low thrust trajectories design. Please.
Значит, основной
задачей проектирования межпланетных перелетов или межорбитальных перелетов с каким-то двигателем малой тяги, в основном, конечно, основанным на некоторых плазменных установках, там или стационарные плазменные двигатели, или ионные двигатели, электрические какие-то двигатели, значит, отличающиеся от всех других, которые применяются в космосе, тоже использующих реактивный принцип движения, это то, что довольно маленькую они развивают тягу по сравнению с гравитационным полем, ну, с силой гравитационного притяжения. Вот. И это приносит определенную специфику и сложность в решении таких задач оптимизационных. Как правило, они получаются сложнее, чем перелеты с большой тягой, которые обычно легко аппроксимируются импульсными приложениями, и двигатель работает бесконечно малое количество времени.
The main topic is low thrust engines used for connection, used for spaceship travels between planets or other objects. The main feature of low thrust engines is that their thrust is considerably low in comparison with the gravitational force, and this changes the mathematical model very essentially. If we consider engines with high thrust, then we can assume that the engine works a very, very little time, considerably with the whole time of the flight. This makes the task and the problem much more easy from the mathematical point of view. But now we consider only low thrust engines, and we will see which mathematical problems arise in this case.
Однако использование таких вот двигательных установок, оно довольно перспективно из-за того, что очень маленький массовый расход и очень высокий удельный импульс или скорость истечения. То есть эффективность этих двигателей на самом деле очень высокая. И набрать скорость и энергетику с ними можно куда большую, чем используя, например, химические двигатели. И особенно это перспективно для перелетов в рамках Солнечной системы, ну, либо на каком-то довольно большом удалении от Земли.
However, the motivation to deal with low thrust engines is that if we compare the effectiveness with the chemical engines of high thrust and take into account the exhaust velocity and the expense of mass, then we see that the effectivity of low thrust engines are essentially higher, especially if we consider flights within within solar system or the same scale of distances.
Эта задача может быть сформулирована таким образом, что у нас есть система динамических уравнений, где x — это положение, v — скорость, значит, омега — это потенциал гравитирующего поля, t — тяга, но особенно m — это масса аппарата, которая непрерывно, вообще говоря, меняется, скорее всего, ну, в смысле, когда работает двигатель. Вот. И также еще очень серьезной сложностью выступает здесь для этой задачи то, что есть некоторая функция дельта, которая является управлением, и она может принимать только значение 0 и единица. То есть двигатель либо работает, либо нет. Ну, соответственно, масса либо расходуется, либо нет. И поскольку для таких задач можно использовать, вообще говоря, только какие-то численные методы решения их, то вот наличие вот такой ступенчатой функции — это еще одна особенная, отдельная проблема именно вычислительного характера.
So the dynamical equations are given. You see x is the coordinate, v is the velocity, m is the mass of the spacecraft, and it is not constant because the the fuel is used. And please look, this delta means the control, the delta in the third equation, and this can be either 1 or 0. So if it is equal to 1, then the engine works, otherwise it doesn't work, but the thrust is constant when it works. This term with this delta leads to certain additional difficulties once you solve this problem numerically, and you always solve this problem only numerically. Since it's a system of differential equations, we have its variational formulation as well, and you see the functional to be maximized.
Чаще всего функционалом в таких задачах выступает конечная масса аппарата, однако, несмотря на то, что на него, на этот параметр, на эту переменную особенно никаких ограничений не накладывается, но на самом деле понятно, что нас интересует только решение, на практике могут интересовать только решения лучше, чем какое-то, заранее задано. То есть мы не можем позволить себе израсходовать, например, больше, чем 99 или 90 или 50% аппарата. И такие решения тоже надо как-то ограничивать.
The functional to be maximized is the useful mass, and it is naturally that it should be somehow restricted from below, because we can't afford to use for the fuel, for example, 99% of the whole mass of the spacecraft.
Приведенная оптимизационная задача в данной работе будет решаться с помощью принципа максимума Пантрягина, который сведет задачу оптимизации к краевой, а краевая задача решалась с помощью метода продолжения, то есть сведения краевой задачи к задаче Каши.
The main steps of the solution are as follows. Of course, we use the Pantryagin maximum principle to maximize the functional. Then we reduce this extremal problem to a boundary value problem for the system of differential equations, and using the continuation method, we reduce the set boundary value problem to the Cauchy problem.
Да, и основные проблемы, с которыми можно столкнуться, решая эту задачу, я уже, в принципе, перечислил. Единственное, что могу сказать, что основное все-таки это отсутствие вообще понимания того, начиная этот процесс решения, существует такое решение или нет. И если остальные проблемы можно решить, работой с численными методами или подбором довольно удачных каких-нибудь начальных приближений, как например, с многоэкстремальностью обычно так поступают, то отсутствие теоремы существования, эту проблему можно решить только каким-то дополнительным анализом задачи, и далее как раз пойдет речь о таком дополнительном анализе.
So if we consider the problem in its traditional posing, then we cannot guarantee the existence of the solution at all. The traditional posing is as follows. Suppose we have two objects we have to connect by our spacecraft, and we have to, so our input data is those two objects, and we have a given spacecraft, so we know its thrust and its exhausting velocity, and our problem is to define even we can ensure that the craft can get from our initial point to the destination or not. And in this posing, the speaker cannot guarantee the existence of the solution, and he is now aware who can. So another posing will be proposed.
Для того, чтобы вот как-то подойти к этому анализу, хотелось бы сделать вот несколько замечаний таких. Значит, это то, что можно ожидать, значит, если вот поставить задачу задаться какими-то параметрами аппарата и искать задачу с фиксированным временем, но оптимизировать тягу, ну, вернее, минимизировать ее, то можно рассчитывать, значит, ну, пока так выразимся, что, значит, такое решение найденное, оно будет такое же, как если бы мы угадали вот с этой тягой и хотели бы с этой тягой решить задачу оптимального быстродействия. Чем эти две задачи хороши по сравнению с предыдущей, когда функционалом выступает масса, это то, что после применения принципа максимума становится понятно, что дельта, то есть функция переключения, всегда должна равна быть единице. То есть никаких вот этих численных неустойчивостей не будет. И это очень приятно. Значит, также еще трудностью может выступать сам расход массы, то есть то, что в процессе решения массу, ну, то есть могут быть только такие решения, которые слишком много расходуют массы. И для начала можно ограничиться вообще случаем, когда масса постоянна. Это тоже очень сильно упростит решение. Вот. А это решение, в свою очередь, можно непрерывно продолжать по массовому расходу или по удельному импульсу или там, по скорости стечения до нужных значений, то есть там, от нуля или от бесконечности, в зависимости, какой параметр выбирается. Вот. И получать сразу целую линию, целый спектр решений.
So the alternative posing of the problem is as follows. The input data is the initial object and the final object, the destination, and the time the latter should be reached from the former. Then we have to find the exhausting velocity and the thrust to solve this problem. This means that we somehow should design a new spacecraft for each new task, but this is real. At the moment, it is done exactly like this. And what are the advantages? First of all, we deal only with constant or step constant thrust, so that delta presented above is still either 0 or 1. So we have to find the value of this thrust, and we have to find certain, well, he called them additional parameters, which are actually means a certain control law to a certain timetable when you should switch your engine on and when you should switch your engine off. And this should minimize this should minimize your thrust. So the previous functional in the previous posing was the mass, and you should the useful mass, and you should maximize it. Now you should minimize the thrust, and the speaker is going to show that these two problems of variational, these two variational problems are in a way dual, and one of the main advantages is that at the initial step we can consider that the mass is constant, and once we solve the problem under this assumption, then we can use the continuation with respect to the mass or with respect to the exhausting velocity, etc., to find various solutions for various cases.
Значит, и вот задача минимизации тяги может быть сформулирована таким же, в общем-то, образом, как и предыдущая задача для минимизации массы. Единственное, что меняется, это функционал.
You see the variational problem to minimize the thrust.
Ну, решается это, в общем, традиционным способом для принципа максимума. Выписывают соответствующие уравнения, гамильтониан. Гамильтониан максимизируется по управлению, и задача сводится там, с учетом, значит, краевых условий и добавления недостающих условий для параметров некоторых.
The variational problem is solved by a traditional method.
К краевой задаче.
So we reduce it to a boundary value problem.
Интересно сравнить задачу на минимум тяги с задачей на минимум времени, поскольку они, очевидно, должны быть очень похожи.
Compare the problem to minimize the thrust with the problem to minimize the time.
Ну, все, в общем-то, делается также традиционным для принципа максимума способом.
The last problem is solved in the same method. And we have the boundary value problem for it.
И вот есть мнение, что эти задачи как бы двойственны. Под двойственностью здесь понимается такая вещь, что есть две задачи оптимизационные, у них разные функционалы, но и разные свободные параметры. В одном случае, значит, свободным параметром является время, в другом случае свободным параметром является тяга.
So this slide shows the sense the speaker gives to the duality of those problems. You see the functionals to minimize are different and the free parameters are different. In the first case, the free parameter is the thrust, and in the second case, the free parameter is the time. But the solution is the same.
Если это так, то можно ожидать, что решение краевой задачи, то есть значения сопряженных переменных для одного и другого случая, будут отличаться на некоторую константу.
If we succeed to find the solution, then the difference between dual variables or joint variables of two problems is just a constant factor.
Ну, это можно проверить, решив одну и другую задачу, а можно попытаться оценить эту константу, оценив интеграл, который в условии оптимальности присутствует, и выразив его, ну, оценив его через значение в некоторой средней точке и связав вот эти вот параметры, которые, по сути, можно отнормировать через свободные параметры, свободно выбираемые константы, которые присутствуют в обоих случаях.
Then he presents the way to estimate that factor G. Алеша, время истекает, пора закругляться.
Ну, а с задачей на, значит, без расхода топлива все еще более просто. Она легко сводится там из предыдущих рассмотренных задач, и условия оптимальности просто немного меняются и упрощаются. Таким образом, можно оценить область существования решения, решив сначала задачу без расхода топлива, потом минимальную тягу, и таким образом сформировать уже какое-то мнение о задаче с какой-то не минимальной тягой, а той, которую мы хотели бы иметь.
The general way to solve the last problem is shown.
Вот на примере перелета к Марсу можно рассмотреть построение этой области существования, которая будет ограничена снизу вот этой вот зависимостью непрерывной, как раз полученной вот, начиная отсюда и до какого-то предельного расхода массы, который мы имеем.
The colored region is an example of the region of the existence of the solution. In this case, it's a technical solution. We can reach particularly Mars.
На этом все. Спасибо.
Thanks for your attention.
Thank you very much. I think we have time for one short question, please.
Траектория у вас линейная? Прямолинейная траектория или нет? Траектория полета?
Нет, конечно.
Is the trajectory a line? Not at all. The answer is not at all. Then you have to know the gravitation change at any point.
Я полагаю, мы его знаем.
We know it.
То есть у вас там получается не одномерная задача, трехмерная?
Да, конечно.
Of course, the problem is 3D.
Okay, one more quick question. This is not the case, so let's thank the speaker again. We should restart it. What a post.
The next generation would be hidden inside a tube. You don't know.
It's good for transport.
Which one?
Moscow.
This one.
Just double click it.
Okay. Oh, this is yes. Okay, I think you know how to use it.
Oh yes, now I know. How to use this?
Pointer,
Perfect.
yes, you see the pointer. Okay.
Okay, the next speaker is Steffen Herting from the University of Heidelberg, and he will talk about dynamically spike solutions in a non-local model of pattern formation. Please.
Yeah, thank you very much. First of all, I want to thank the organizers for giving me the opportunity to present this. The presentation is based on the joint research with Anna Marciniak-Chokra of University of Heidelberg as well, Grzegorz Kaj from Wrocław University, and Kanako Suzuki from Ibaraki University, which is in Japan. And, well, this is very much motivated by biology. So the model actually, using this type of model for the description of biological phenomena the idea comes from Marciniak-Chokra. It's so-called receptor-based models. So what do we have? I mean, we have some biological, let's say this is a tissue, and we have some cells, and the cells have some growth factors which they produce and which they, well, you can say consume. You can say that they get some signal, or you can say that they consume them to produce something or to grow. And by themselves, they also produce those growth factors. Those growth factors are assumed to be diffusive. And if you assume that the blue ones here, these blue circles, are cells, and what's in between are growth factors, and you think that These blue circles are part of the domain, and in there the growth factors diffuse. You can use homogenization. This is what Professor Marciniak-Chokra has done, and you end with a model of this type. So basically it's an ordinary differential equation, which is used for describing the not dynamics, but like the growth behavior of the cells, and W, which is describing the concentration of the growth factors. So this is the motivation from biology. So let's take a look at the equations. And if we take a certain model, which comes from biology for the modeling of Hydra and also like the complex of Wind, LRP6, which is a receptor on some Hydra cells, then you reduce the model, then you get this model. And I mean, I don't want you to exactly look at the nonlinearities. I mean, you can do that, but it's not so important. Because first of all, we use some numerical approximation to look how the solution behaves. This is in the time, and here is the spatial variable. So what we observe is that actually in numerics we see a concentration of cells at some single point, and I mean you cannot see it here because the scale is quite high. They die out at on the rest of the domain. So the model itself exhibits diffusion-driven instability. Well, if this would work, okay. Has diffusion-driven instability, mainly meaning that the ODE system, we assume that there is no diffusion, then there's a spatially homogeneous steady state which is stable. So let's assume that this U bar is the steady state. I mean, if it's constant, then the diffusion vanishes. So this is definitely also a steady state of the PDE system. But the point is that with respect to perturbations which are spatially homogeneous, like this blue one, it's stable. And with respect to perturbations to spatially inhomogeneous, like the red one, perturbations, it's unstable. And this idea basically goes back to Turing, who wanted to use it to model, something like Hydra, for example, like pattern formation in biology. Also, it's possible to prove that all non-constant steady states are unstable. Well, the question is what's happening if the diffusion coefficient is positive, so this one is unstable, and all non-constant steady states are unstable. The trivial steady state is stable, but in numerics we cannot see that it's converging to it. As you remember, it has this nice spike solution. So, but this was proved by Marciniak-Chokra, Karch, and Suzuki, and then later I joined them. The open problem, which is still an open problem, is the blow-up, proving the blow-up of this system analytically. So we tried this for, let's say, about 1 year, and then we asked ourselves, well, maybe let's look at what happens if diffusion tends to infinity, or if the cells somehow react very, very slowly. I mean, that's particularly equivalent. So we see that if we increase or let the diffusion coefficient d tend to infinity, then in some sense the solution converges towards the solution of the so-called shadow system. So, so it means that the diffusion just gets bigger. So let's take a look at these equations. And first of all, there is some very nasty condition. It basically means that we need to have a uniform bound on the solutions in time and space this is why we have this finite interval. So we have this d-independent bound. And the question, of course, is in which sense does it converge, because the initial conditions of the shadow system, one was just constant, and the initial conditions of the PDE is non-constant. I mean, in which sense do we observe conservation? And it's exactly in this sense. So let's say the solution is allowed to do funny stuff in its youth, but later on it just like behaves similar. So, also, as I said, we have diffusion-driven instability in the PDE system, meaning that the constant steady state gets destabilized if we introduce diffusion. Well, we want this to behave similar, so it should be stable. I mean, obviously it's stable, because if it's constant, then the integral term is just some constant. I mean, it's integrating over a constant function. And we want the destabilization if the diffusion, if the integration is introduced, as when the diffusion is introduced in the other system. And this is exactly what's happening. I won't give you the proof of this, I just want to show you that it's behaving similar. The proof is basically, it's not that complicated, it's finding a spectral gap. Well, using some theorems you can find in Henry. And it has exactly the same behavior. So, we want to ask ourselves, okay, and this theorem was rather general. For F and G and C2, it's okay. We want to ask ourselves what's happening if we take a look at the specific model, at the carcinogenesis model I presented in the beginning. So it's this one. And, well, applying exactly what I showed before is basically just an integration instead of the diffusion term, meaning that if we take, without loss of generality, the domain to have measure 1, we obtain exactly this equation. And we put it by side. And remember that this system had a blow-up in this one point in numerics, not in analysis. I mean, maybe it has it in analysis, but we couldn't prove it until now. So now, for the proof, we had to assume some very, well, let's say technical conditions on the initial conditions, which I want to explain to you in a picture and not by the equations, because it's rather intuitive what this means. This basically means that we're not allowed to have a maximum which has a non-zero measure. Means it's not allowed to have a plateau at the very top of the initial conditions. Also, it's not allowed to start very small for u. And the psi must be very small. This is basically what it's saying. So either it's allowed to have a very spiky initial condition, or it must have very large initial conditions for u. So what's the idea? The idea is that it's not very complicated to prove that if at this x star is the point of the maximum of the initial conditions, or where the initial conditions assume the maximum, at this point, I mean, oh no, this is not the assumption, this is the result, sorry. At this point it goes to infinity, and at all other points it stays bounded. And the psi, it's the other component, just for completeness, I write that it's tending to 0, but this is not very interesting for the pattern formation itself. So the idea of the proof is that first of all, we prove this very technical condition, which basically is similar to the condition of the initial condition. So it means that the initial conditions satisfy these conditions, then the solution will satisfy it. We have, keep it in mind, some comparison principle, because we have a unique solution of the first equation. If we only look at the first equation, means that if this is, at this point, the solution has a higher value than at this point, then it will always stay higher. And we're able to prove that the mass of the square of the function has a minimum, basically meaning that, which is strictly positive, meaning that whatever is in here needs to somehow fit in there. And this is basically this. And also, the maximum is usually higher, the square of the maximum is higher than the mass of the square of u. So, yes, so this means it cannot tend to 0. If it cannot tend to 0, or it doesn't go to infinity, we can prove that all other points tend to 0. But we can prove that there is a supremum. We have a minimum of the mass of the u square. So basically meaning that, well, it must tend to infinity, because otherwise the mass would tend to 0. But that's not possible because we have a minimum mass, which is strictly positive. Also, we have a supremum on the mass of u, so it's L1 norm in this case because I have a strictly positive solution. And because of that, everything what's in here needs to fit in here. Basically meaning that these cannot tend to infinity because we have the comparison principle. And then we ran some simulations. I mean, this is just some illustration. I mean, oh, I'm very, very fast. Incredible. I haven't planned it that fast. So we can see that if we assume initial conditions of this shape, as in the beginning, we have a single spike here. If we assume initial conditions, which has like two local maxima, like here and here a bigger one, well, both at both points, at this point and at that point, or not exactly at that maximum, but if they have equal initial conditions, then they say that they satisfy the same initial boundary problem. Anyway. So this needs to tend to 0 because this point tends to 0, or this point tends to 0, so this point needs to tend to 0 too, because it's basically an ODE. If we take them with the same value of the maximum at both points, so it's like periodic, then we have two spikes. I mean, also kind of obvious. I don't know if it's obvious, but it's kind of intuitive. And if we take a plateau, this was the forbidden initial conditions. Then we see also in numerics that the solution is bounded. Well, and in the end, at the end, I want to point to this problem because maybe someone has a nice idea to solve this, because we were reducing this model to this integral differential, or to this shadow system. And for that we could prove that we have a blow-up. But until now we're not able to prove that this system has a blow-up in this point if this system has a blow-up in this point or at any point. And that's basically the problem. What's possible is to prove it for systems of Gray-Scott type, for example. But for this particular system, which is for us the most interesting because it really comes from the modeling of biology, we cannot prove it. Also not using the same techniques as for the Gray-Scott system. Okay, so if anyone has an idea how to prove that, feel free to mention it. Otherwise, I want to thank you for the attention, and yeah, we'll give space.
Thank you very much for your talk. Are there any questions or remarks? Suggestions for proof?
That would be nice. Well, in which sense do you mean energy? Like you mean some energy functional and then it's decaying?
Yeah, some Lyapunov function.
No, we're not able to prove that. Unfortunately, that would be nicer, I mean, than in L1. Okay, in some sense, no, it's not in some sense, but let's say the L1 norm is bounded, so you have a chance to maybe prove it, yes.
Further questions? This is not the case, so let's thank the speaker again. And we continue in 10 minutes.
Damit habe ich nicht gerechnet. Jetzt, weil ich das durchgegangen bin, habe es 20 Minuten gedauert. Bitte? Jetzt, weil ich durchgegangen bin, habe es 20 Minuten gedauert. Was passiert? Das ist, und man wird man so schnell und dann... Wow, last time I practiced was 20 minutes.
Попробуйте, вот тут есть перерывчик.
Спасибо.
So it's time to move on. Our next speaker is Georgi Kitavtsev from the Max Planck Institute in Leipzig, and he will speak about coursing dynamics of droplets driven by thin film type equations.
Thank you very much for the introduction. I would like to thank organizers for possibility for me to present talk here at this wonderful workshop, and thank you very much for coming so late to the last talk today. I will try not to bore you too much and to be quick. So basically, I will speak about coursing dynamics of drops, but the key thing here is governed by a thin film type equation, which is fourth order degenerate parabolic equation, which analysis is quite complicated and separate area of research nowadays. It's a joint work with my PhD supervisor Barbara Wagner, and Barbara Niethammer, and some other people. So basically, physical model for thin film type equations that you have a film, liquid film on a solid substrate with a free surface parameterized by a function h, depending on time and space. And we look in evolution of free surface in time, and basically it's driven by surface tension as usual. If you have an nanometric film, that you should include intermolecular interactions of the fluid and substrate. In a macroscopic model, usually people introduce so-called disjoint pressure, Leonard-Jones type potential, first part of which is van der Waals forces, and second one corresponds to Born repulsion terms, which prevent film from a full rupture. So it's so-called precursor model, which I'm dealing with. And the last but not the least effect, it's a slippage. It's a prescribing velocity of the liquid on a solid substrate. Also, it's locally, it seems as a boundary condition, but influence globally on the flow. As you see, if you have no slip, you have a parabolic flow, increasing slip. So roughly speaking, to infinity, you come more to the Planck floor, where velocity doesn't depend on a vertical direction. So there are many applications of these processes in chemical and mechanical engineering. Thank you very much. Basically, if you initiate holes in the film, it starts quickly to rupture. If you have these intermolecular interactions, you cannot rupture up to the substrates, and you are separated. You have a region separated by very thickness of order epsilon, which is a key parameter in my analysis now, which is very small. And in the end phase, you have drops forming, which start to interact with each other and course. That means the number of drops decrease in time. Usually, as you see on this from the top of, in this experimental picture, the number of droplets increase in time, and this average size of drops increase. And you see it's very slow process, about days, sometimes even months. And the main interesting question we're asking here, what are the coursing rates? It means how fast the number of drops decrease in time, also slowly, and what are mathematical understanding of a driving mechanism of this coursing. Basically, we saw in numerics and experiments it can happen only by two mechanisms, so-called collapse of drops, when smaller droplets dissolve in this ultra-thin layer of order epsilon, and their mass is gained by bigger drops. And second mechanism is the collision of neighboring drops, where the big drop come to each other, join and form a bigger drop. So for mathematical analysis of this problem, usually people start from Navier-Stokes equation with conservation of mass. Nano-thickness of the film allows this system to be effectively reduced to so-called lubrication equations, which depends on a slip range which you have at the substrate boundary. But for analysis of the coursing dynamics, it's even more effective to reduce these lubrication equations further to so-called finite dimensional models, reduced ODE models, which I speak about in this talk. And I will give a certain example when you can solve these reduced ODE models explicitly. a very specific example which corresponds to so-called free film model, or basically to infinite sleep regime. So as I said, lubrication equations depends on a slippage. So there is a so-called more or less classical form, which we call weak sleep models. They are valid for when your slippage on the solid substrates is not very big. And from this model, you can derive all classical models as a limiting case. For example, no sleep case, it corresponds when the sleep length B in the left model is equal to 0. As the right model is valid when a slippage is large. That means 2 magnitudes larger than in the left model, asymptotically. And it has a different structure. It's a coupled system of evolution of average lateral velocity U and height profile H. What's common for both systems is a disjoint pressure, or this hydrodynamic pressure, which is just sum of linearized surface tension or curvature, and this Leonard-Jones disjoint pressure, which I talked at the beginning. And asymptotically between these two models, there is a classical Navier sleep model corresponding to mobility H squared. It can be obtained either you tend B in the left model to infinity and rescale time, or you tend beta to 0 in the right system, and again rescale properly time. And in both cases, you end up with this Navier sleep case. So it makes a bridge between these seemingly different models, but they somehow have an interesting connection, which is also important for establishing weak solutions for the right model, and thinking about dissipative properties like energy, entropy, decay for these models. So it's interesting, surprising result that these models also looks differently. So you have additional viscosity term here, which is also degenerate. You have inertia terms from Navier-Stokes system, which we retain from Navier-Stokes system, but this common pressure term makes this classical lubrication models and this strong sleep model mathematically related and also physically related models. So just summary on these two models, they were derived about 10 years ago. Surprisingly, the right model was derived even much earlier. It comes from a free film, as I said, and viscous jet systems community. And we established the existence of weak solutions. And this convergence to the classical solutions of Navier sleep case. When slippage goes, beta goes to 0, as I said, you recover this Navier sleep case. And concerning coursing dynamics of drops, this late stage evolution, there are a lot of works already for the weak sleep models. For example, by Felix Otto and Glasner and co-authors. They showed basically that this left model, weak sleep model, course also with the exponent minus 2/5. And so what were interesting from the beginning, if to check that the right model system, which is more complicated, has the same coursing rates, and it turns out that's not. And actually it has a diverse range of coursing rates. So basically to describe coursing, you should look at the stationary solution of your system. Again, for left and right systems, you have the same family of stationary solutions, which are solutions of this ordinary differential equation with two parameters, epsilon, fixed, and pressure. It's called pressure because it's really, if you look, it's defined as a constant hydrodynamic pressure, which our stationary solution, this pulse or droplet possess uniformly. And dynamically, this system of solutions corresponds to periodic solutions inside of a homoclinic loop. And as I said, about 10 years ago, for the weak sleep models, this is called reduced OD models, were derived by Glasner and Wojciechowski in this closed form. Basically, if you look at these droplets, they are quasi-stationary and weakly interact by small fluxes between them. As I said, they have an almost constant pressure inside, which we parameterize for each droplet by this set of PGs, and they are characterized also by the position in time, which evolves slowly, this G, and you have a closed evolution of the pressures and positions of n droplets, and the right-hand side basically non-linear, depends again on the pressures and positions. In the weak slip case, it's just difference of pressure divided by the distance between drops. So it's this dj is just distance between drops, which you should keep in mind. There are many approaches to derive this OD model, so I thought that for this workshop the most interesting, and for people coming to this workshop, dynamical system approach via so-called center manifold reduction type approach, which originates somehow from recent work of Alexander Milky and Sergei Zelik, which they derived for broad class of semi-linear parabolic systems. In this case, we have a more general system which is quasi-linear and degenerates. This makes additional difficulties, but still, at least at some level, this approach works also here nicely. So you consider this, for example, I will speak now about classical lubrication models or weak slip models with the Neumann boundary conditions at the fixed interval. I denote the right-hand side this quasi-linear elliptic operator by f of epsilon. If we define a set in R2n of pressures and positions in which our droplet parameters can vary in time with some constraints which are not so necessary now to understand. And if we define so-called multipulse structures, which is map of this set to L infinity space by the superposition of stationary solutions, which are known functions for us and depend again on the position and pressure of the drops. So we just use sum over with some smoothing cutting procedure stationary solutions corresponding to different pressure and positions, and obtain this sum, which is called M of epsilon, this mapping. One can define an approximate invariant manifold, which is just image of this M of epsilon. It's 2n dimensional. You can show that this M of epsilon establishes the diffeomorphism between our parameter set and this approximate manifold in L infinity space. Sorry. You can define a tangent space naturally by partial derivatives of our multipulse structure with respect to pressures or positions. And why it's called approximate invariant? Because the right-hand side is very small. It's order of epsilon 3/2. So it's better even call it approximate stationary manifold, not invariant manifold. So it means if you are in the neighborhood of this manifold, you move very slowly, and this is natural because coursing is very slow. The main ingredient of our approach is to define so-called adjoint functions, which are orthogonal in L2 product to our tangent functions, and to construct special projection mapping for each point on the approximate manifold. You have a special projection operator defined with a span of tangent functions with the special coefficients which depend on these cotangent adjoint functions. The main results which we show that if you consider a small tube around this approximate manifold of certain order of epsilon to some power, each point in this tube you can decompose, you can find the corresponding so-called point on exactly on the manifold M by means of this nonlinear function p epsilon, so that the remainder is small, v, and moreover its projection, which we defined, so projection operator at the point M applied to this remainder v is exactly 0. So more or less in the Euclidean space it would just be orthogonal decomposition of a point near manifold on the point on the manifold and its orthogonal component. So basically for people who are okay, so I just wanted to show how it's works for trajectories in a finite dimensional case, but maybe people here know this kind of center manifold reduction. So I accuse this picture doesn't work now. So it's maybe later I will show it at the end, but now it's not so important. So, but the main thing is that you can decompose your parabolic quasi-linear equation, this lubrication equation, into two coupled systems. One is for the evolution of the point M on the manifold and evolution of the remainder V. And as we show, the remainder evolves very slowly, and this right-hand side almost zero, you can, to the first order approximation, look just at the system evolving on the manifold, putting V to 0. And this should give us our reduced ODE system, because manifold is 2n-dimensional. And explicitly writing this base system, zero-order system, and multiplied with the joint function, you end up with the same closed form which I just showed you, derived by Glasner and Vitelski by formal asymptotic methods. And moreover, we recover also coefficients depending on our parameters G, C, and P, explicitly in the same way, and also fluxes. So basically, fluxes are described by this so main part of our elliptic operator estimated at the point on the manifold, and this has explicit form, and which is also to the leading order the same as Glasner and Vitelski derived it. So if you ask me how to prove this, to accomplish this proof rigorously, so to construct central manifold near the approximate one, which is really invariant. So basically, you should go further and look at the spectral properties. I don't know if people here are interested, but the interesting thing, as I said, we have a degenerate system, and this degeneracy reflects also in the spectral properties, because when you want to show a spectral gap property, you see that there are finite number of small eigenvalues, exponentially small, for example, for one pulse, and the rest still small with respect to epsilon. So the rest of the spectrum behaves, but it's algebraically small, like epsilon squared. And when epsilon goes to 0, you have a special singularity that the whole spectrum tends to 0. And so it's not a classical spectral gap, which you would expect when it has a finite length, doesn't depending on epsilon. So this makes this problem, the spectral gap behaves like epsilon squared. And the application of Milky-Zelek algorithm is not straightforward here. It's much more delicate. But our main result was to describe the spectrum, because it's the first step which you would make before to establishing the manifold rigorously, central manifold rigorously. And it's a separate interesting problem. You end up with a fourth order eigenvalue problem with the special coefficient functions depending on your stationary solution. And as I showed on the picture, the main result is that you have one exponential small eigenvalue, and the rest of the spectrum behaves algebraically like epsilon squared. So if you're interested, you can ask me a question about spectrum at the end of my talk. But returning to the ODE systems, we also derived the same ODE systems for the strong slip model, if you remember this right system, when I showed lubrication models. It has the same closed structure, but different coefficients and different fluxes, different dependings of fluxes on pressure and position. And what was interesting, now this viscosity parameter, which was absent in a weak slip model, comes into play, and explicitly the flux depends now not just on the pressures and positions, but also on the velocity of the droplets. So the structure is more rich, and taking viscosity to 0, you can recover ODE system of Glasner and Vitelski also as a limiting case. And just to illustrate that this ODE systems works well if you take finite number of drops, you solve your PD system and look at the pressures inside of the drops. You know that they are evolving slowly in time. And then you solve your ODE system with the same initial condition and map solution, which is a solution of ODE system is given by dots. On your PD solution, you see the precision is very nice. It's order of epsilon as expected. So epsilon here is about 0.02. So the precision is very nice, and this works for different sleep lengths. That's why people are so interested to simulate coursing via these ODE systems, not via PD, which is quite stiff and difficult to solve. And I don't know how many minutes I have. 0. Okay. So I just wanted to say that there is a very special case corresponding to beta equal to infinity when you can solve this ODE even analytically explicitly. And you can, yes, this is explicit solution for n number of drops. And you can derive, taking number of drops to n to infinity, quasi-thermodynamical limit. You can derive continuous coursing rate, analytical coursing rate law, which gives you which time do you need to absorb all the drops with the distance to the neighbor smaller than d explicitly. It's interesting, it comes out as kind of relative entropy formula. And moreover, you have a diverse range of coursing rates, as I mentioned at the beginning, for different sleep lengths. For example, in this case beta equals infinity, you take different initial condition distributions of your drops, just differing by algebraic decay at infinity, and you have switch between exponential and algebraic coursing rates. So, yeah, so sorry for this general introduction. If you have questions, you can look in this article, so ask me. Thank you very much.
Thank you very much for the interesting talk. Are there any questions? Remarks? Everybody's tired?
I understand them different mixture of what coercions here. It is equation of thin film, liquid. What coercions? But you have some different kind of drop.
Yeah.
What coercioning is dividing of different phases. What coercions here?
Coercions here.
Not in this model. What coercions?
Okay, so you can think as a geometric coarsening size is the radius of problem. So the geometric parameter which course in time is the average radius of the drop.
Drop is coercion in the sense that it moves, some droplets moves, different droplets.
They join and some of them disappear, and the average size of the drops increases in time slowly.
This mechanism you call like the coercion.
You have explicit coursing parameter.
Clear.
One more question? This is not the case, so let's thank the speaker again. And this is the end of our session. Thank you.
So the conference is over. Let's thank our chairman.